Good morning, everyone, and welcome to MV Tutors. I'm Tsulu, and I'll be looking at question 1 with you guys. You're probably looking at the question paper and you're like, Mara Tsulu, that is like a question paper from 2020. We just wrote the prelim now, 2021. Well, our government decided to take last year's version 2 of the paper 2 exam written in November. So when they compile exams, you have revision 1, which they normally write, and if anything goes wrong, there's another revision waiting. Okay, so revision 2 was decided that it was going to be used for this year's Gauteng Prelim paper 2 exam. Okay, so please bear with me. But yeah, let us see what it contains. And guys, please don't forget to like our videos, subscribe to our channel, and also tell a friend about our channel where we learn physics and maths, specifically for matriculants. Also tell your parents to come in and see what's happening, just in case you want to book a lesson with us so that they can see how we actually deliver our services. Okay, let us look at question 1, multiple choice. Alrighty, so 1.1, which one of the following is an alkane? Okay, so they give us the molecular formula. All right, guys, you know the general formula of an alkane is actually CnH2n plus 2. That is for the alkane. If you want it for the alkene, it's just going to be 2n. And if you want it for the alkyne, it's going to be 2n minus 2. Okay, so we need to have a look. Let me just leave the one for the alkane because that's what they asked. If we look at A, well, we have 6 carbons and 8 hydrogens. Nope, that's not going to work. We need something that is at least more than twice. Okay, more than twice the number. We need hydrogen atoms that are more than twice the number of carbons. So if you look at B, we have 6 carbon atoms and 10 hydrogen atoms. So that's not going to work. Okay, so basically if all our carbons are 6, if we substitute 6 in there just to save time, we will have to say 2 times 6 plus 2, and then our answer will be 12 plus 2, which is 14. Okay, yeah, I didn't actually realize that all the carbon atoms were 6. So yeah, if I had seen that earlier on, we would have just started from there using the formula and then getting what the number of hydrogens should be. So as you can see, D correlates to what we have. Okay, so D would be the correct molecular formula for this alkane, and this alkane would be hexane. Okay, because there are 6 carbon atoms. All right, and then 1.2, esters are formed by a reaction between 2 organic compounds, X and Y, each with a different functional group. Do you know what they are? Yeah, so basically we have our alcohols. Basically, when you name an ester, you first start with the alcohols, and then you name it according to the carboxylic acid. So those are the 2 functional groups. Carboxylic acid. Okay, so you need alcohols as well as carboxylic acids to form an ester. So from the alcohol, we have your hydroxide group, and for the carboxylic acid, you would have your carboxyl. Remember how you identify carboxylic acid? Cu and OHO. So Cu-O. Cu. So having a look at 1.2, yes, compound X is the hydroxyl group. Okay, so yes, we're looking at A and B. And then when you look at compound Y, it cannot be the carbonyl group, it is the carboxyl group, hence carboxylic acid. Okay, so we are looking at A as our answer. Okay, remember esters? Oh, cool. Yeah, alcohol and carboxylic acid. Do not forget it. Okay, now 1.3. When butane is subjected to high temperatures and pressures, the following reaction takes place. Okay, do you guys realize what this reaction is? Well, it is an elimination reaction. When you start off with a saturated compound like an alkane, and at the end it breaks apart, okay, through the elimination process, we call it cracking. Okay, so you start off with an alkane, or rather you start off with a saturated compound and you end up with an unsaturated compound. Okay, so we have butane there. So butane, we know that it is 4 carbon atoms. I'm just going to put the structural formula. I'm not going to put the hydrogens, guys, or else we're going to take forever. So we go from butane to methane. Okay, just to start off with, butane has 4 carbon atoms, and because it is an alkane, it must have 10 hydrogen atoms. Okay, then we have methane. Methane has 1 carbon atom and 4 hydrogen atoms. So what must Y be? Well, let me tell you for now that when you are actually partaking in the cracking process, when you have an alkane, obviously we'll start off with an alkane because it is unsaturated, it is saturated. Your results, or rather your products, it will be an alkane and an alkene. Okay, but I'll show you now. So we had 4 carbon atoms initially, 10 hydrogen atoms initially as well. And then you removed 1 carbon atom and 4 hydrogen atoms. So what are we expected to be left with? We are expected to be left with 3 carbon atoms. Okay, and how many hydrogen atoms? Well, 10 minus 4 is 6. Okay, and remember the formula, the general formula of an alkene. It is actually CnH2n. So you can see here that we definitely have an alkene. And that alkene has 3 carbon atoms. It is a double bond as well. Okay, so yeah. So now what do we say about it? In the first, or on the first carbon, if you're going to write out the condensed structural formula, which is what they actually gave us, your first carbon has 2 hydrogens. Your second carbon has 1 hydrogen, and your third carbon has 3 hydrogens. So we're going to look for a condensed structural formula that is representative of what we have. So the first carbon, no, A, that will not work. We either start with 2 hydrogen atoms or 3. Okay, so B, we have CH2, CH3, yeah, CH3, so that is correct, definitely. C and D, no, they do not count. All right, now we go to 1.4. What is happening there? Okay, so a hydrochloric acid solution of concentration 1 mole per cubic decimeter is added to excess powdered magnesium at 25 degrees. Do you see those are standard conditions? Remember your standard conditions, your concentration is 1 mole per cubic decimeter, temperature is 25 degrees, and if you have gases, the pressure would be 1 atmosphere or 101.3 kilopascals. So we have standard conditions here. Now curve 1 below represents the volume of hydrogen gas produced during the reaction. Curve 2 was obtained at different conditions using the same volume of hydrochloric acid solution. Okay, so everything else remained the same, right? For curve 2. Oh, it's just the same volume. Okay, it's the same volume. But what we can then say, if we're looking, okay, the question says, which one of the following represents the conditions used to obtain curve 2? As you can see, curve 2 is much steeper than curve 1, okay? And looking at our answers, one thing that I do know is we have powder, okay? I don't think we have a ribbon. Magnesium is in powder form. That excess magnesium is in powder form. So we're looking at C and D. Now, curve 2 is much steeper than curve 1. Okay, the y-axis is the volume of hydrogen gas produced. Do you see, actually, you know, when you look at a gradient, you're actually kind of looking like at the rate at which something occurs. Okay, if your gradient is flat, it means it takes quite a while to get to where it needs to get to. But if it's more steep, it's happening at a faster rate. So when I look at this question, I'm thinking of the rates of reaction, okay? And what is it that gives you a higher rate of reaction? We can see that curve 2 actually is happening at a quicker rate, okay, because of the gradient. So when we're looking at rates of reaction, we're looking at the surface area. We know it's powder for both curve 1 and 2, so that's fine. We're looking at temperature. The higher the temperature, the higher the rate. We're looking at the type of molecules you have. Well, they're the same, the same volume still of hydrochloric acid. What other rates of what other factors are there? So yeah, concentration as well. If you increase concentration, then you'll get a higher rate. So yeah, looking at your theory as well, you'll get that. So now, like I said, we're looking at option C and D, okay? They're both in powder form. Magnesium is in powder form. The concentration of the acid, well, it's the same volume. Remember that calculation, concentration is equal to number of moles over volume. So I'm assuming if it's the same volume, then the number of moles have remained the same. Therefore, the concentration is also the same. But what would make curve 2 steeper? Temperature has increased. Okay, so you started off at 25 and now you're at 30, and that is why it is steeper. So I would go for option D. Okay, I believe that is where your rates of reaction will come in. So yeah, let us take a young break and we'll continue with 1.5. Everyone, and welcome back. So during the break I decided, let me just write this out because I realized it'll be time consuming. Okay, let's read 1.5 and I'll explain what it is that I've written down. So now it says, in which one of the following reactions at equilibrium will the yield of the product increase when the volume of the container is increased at constant temperature? So guys, if you are going to increase volume, what happens to the pressure? The pressure will definitely decrease, okay? Yeah, because increasing the volume, you have a very huge space. There will be like less pressure, okay? So now, when we use Le Chatelier's principle to talk about what happens when you change the pressure, okay? Basically, what I've written there now, if you have less pressure or you decrease pressure, which side will the reaction be favored? Well, basically depends on the number of moles. So if you have an increased, if you're looking at your reactants and you're looking at your products, if you have more moles on the product side, your reaction will be product favored for the case where you have low pressure, okay? For the case where you have higher pressure, you get to look at your products and your reactants and you get to see how many moles do I have. So the least amount of moles, whether on the product side or on the reactant side, that's the one that you choose. The lowest moles go with the higher pressure, okay? The lowest pressure goes with the highest number of moles. All right, I hope I made sense, but I will show you here with this table that I've drawn. So the scenario that we are looking for, they told us that the volume is increased. So if the volume is increased, it means the pressure has been reduced. And as a result, we are looking at this first condition over here. Okay, so now, looking at the number of moles, for A, on the reactant side, you have 1 mole, right? So I'm going to write there number of moles for the reactants, 1. Okay, so what we are looking for basically, we're looking for a scenario where the products have a lot of moles. In that case, we know that it will be product favored because they did say they want a high yield, okay, of the products. So for A, 1 mole on the reactant side, and we have 2 moles on the product side. So this one seems to be winning so far. B, we have 2 moles on the reactant side because you have 1 mole of hydrogen and 1 mole of iodine. So you have 2 moles, and then on the product side, you also have 2 moles. So this doesn't work, okay? According to Le Chatelier, it'll be like confused. Who am I favoring? Reactants or products? So we're not considering that. And then for C, you have 4 moles on the reactant side, okay? 1 mole nitrogen and 3 moles hydrogen. And then you have 2 moles for ammonia. So here, this is reactant favored, and that's not what we want. We want something that is product favored. And then the last one, we have 3 moles on the reactant side and only 2 moles on the products. Again, reactant favored. So our answer will then be A. Okay. There are other conditions to think about, like if you have an exothermic reaction, what happens when you increase temperature or when you decrease? Where is the reaction going to be favored? If you have an endothermic, what did I say before? Exothermic? But anyway, it depends. Exothermic, endothermic, how does temperature affect that? Then there's a question of how does concentration become affected if you increase the reactants or you increase the products. Using Le Chatelier, how will that reaction, which side will be favored? But here we're just covering the pressure side of things, okay, because we have gases. All right. If we didn't have gases, we'll probably have to look at concentration. And if they had told us about temperature, then we would have had to look at temperature conditions. Okay, 1.6. Which one of the following statements is true for an exothermic reaction? Okay, so let us say you have on your reactant side A and B, and then on your product side C and D. How do you know that something is endothermic or exothermic? Well, basically, if you need to add heat on your reactant side in order to get the products, if you need to absorb heat in order for the products to form, you have an endothermic reaction. Okay, so that is endothermic. And remember also your enthalpy is bigger than 0, so you'll have a positive enthalpy or change in heat. Okay, but if you have an exothermic reaction, you are going to release heat or energy, okay, on the product side. So as the products form, heat is released into the environment or energy. Okay, so that is for exothermic reactions, and your enthalpy is less than 0. Okay, you always have negative. All right, and if you were to draw a graph indicating an exothermic reaction, well, basically, you don't really need much heat at the beginning, but more at the end, okay? And that indicates your energy, potential energy, that would be time, okay? Whereas for an endothermic reaction, you require more heat at the beginning, but at the end, you know, it's not a big deal. All right, so what are they saying? So, option A, more energy is absorbed than released. No, that is applicable for an endothermic reaction, not exothermic. Okay, so that is out. And now, B says more energy is released than absorbed. Yes, if you look at the exothermic, more energy is definitely released. Okay, you have more energy this side than you required on the reactant side. So yeah, B is definitely winning so far. Okay, now it says the heat of reaction is positive. No, that is for the endothermic reaction. And then it says the energy of products is greater than the energy of the reactants. What do you think? It sounds about right, ne? The energy of the products is greater than the energy of the reactants. I mean, look at this. Isn't the energy of the products over here greater than the energy of the reactants. Okay, I think the trick here is about energy being released and energy being absorbed. Okay, I think that is the main thing about exothermic reactions. The energy is released to the environment. So I would go with the released, more energy is released than absorbed, rather than the energy of the products themselves is greater than the energy of the reactants. Okay, yeah, hey? So I'm gonna say B in this case. Okay, and then let's go to 1.7. Consider the equation below. So we have H3PO4, I forgot the name, the actual chemical name. I don't think it's phosphoric acid. Anyway, so we have H3PO4 plus water gives you hydronium ions and H2PO4 ion. All right, so now which one of the following is a conjugate acid-base pair? Let me just rewrite this. Or maybe not. Let me just make notes on the question paper itself. So, this is like a strong acid, okay? That's what I know. It's a strong acid. And then we have water. Water can be an acid or a base depending on what it is reacting with. Okay, so in this case, water will be the base. Remember, water is an amphiolite. So it can be both. It swings both ways. So now, if we have an acid over here, its conjugate base, remember acids, according to the Bronsted-Lowry theorem, is one that donates protons. Okay. Yes, I hope I'm not saying the wrong thing here. So it has, no. Never mind. Yes, it donates. So now it's left with 2. So if this is the acid, you now have this conjugate base. Okay? Yeah. And now a base is basically a proton acceptor. Okay? So you have H2 and now you end up with H3 because it has received. Okay? So if your base is here, this is going to be your conjugate acid. Okay. Yeah. So that's your conjugate acid base pair. Now let us have a look at the options that they give us. Okay, if we have a look at A, yes, our conjugate acid is it is H3O, the hydronium, and the base is water. So definitely A is winning at this point. B, no. If you have H3PO4 or H2PO4 somewhere, no, wrong. So B out, C out, D out. So you have A as your solution. Okay, so let us take a young break and then finish off the last 3 questions strong.
You might have more talent than me. You might be smarter than me. But I will not be outworked. Period.
Welcome back. We are going to go into question 1.8. Okay, so consider the balanced equation for the reaction below. I think I'm going to make notes here. And then they're asking which one is the oxidizing agent. Okay, let's have a look. Okay, so we have 2 chromium here. Ne? It has 2 plus ions, so it has excess protons. Okay, and if we look at this side, the chromium, it has more protons, so meaning an electron it lost an electron. It lost an electron. So from here to there, okay, it lost an electron. And what do we call those elements or compounds or ions that lose an electron? Okay, when something is oxidized, it loses an electron. Okay, so chromium here was oxidized. Okay, just gonna say oxidized. And if it is oxidized, chromium, if it's oxidized, it's actually a reducing agent. Okay? Yeah, oxidized, it became the reducing agent. Now, let me just change the color. If we look at tin, Sn, it started off with excess 4 protons, or 4 excess protons. And then we had only just 2. So it gained electrons. Okay, so from tin 4 plus to tin 2 plus, it gained electrons. And the process for gaining electrons, we call it reduction. So it was reduced. So tin was reduced, and as it reduced, it became an oxidizing agent. Okay, now, which one then is the oxidizing agent? Guys, it's going to be D, okay? Yeah. And then we get to 1.9. So, an electrochemical cell is set up at standard conditions. Standard conditions meaning concentration 1. Okay, let me just put it there. So standard conditions, your concentration is 1 mole per cubic decimeter. Your temperature is 25 degrees. Your temperature, again, it is 1 atmosphere. So we have the cell notation for the cell given below. Okay, so on your anode, remember when we write this kind of cell notation, you start off with your anode. Always, always, always start with your anode. Don't ever start with the cathode. Okay, so magnesium, that is on your anode, it's a solid, okay, and in solution, it is oxidized, and then it becomes magnesium 2 plus. Then we have our salt bridge there, and then you have lead, and then the lead solid, which keeps gaining as the magnesium solid reduces in mass. Okay, so what is happening here? The cell is now connected in a circuit. Which one of the graphs below best represents the concentrations of the electrolytes after a long time? Okay, so guys, if we look at A, well, A is showing that nothing is happening, which is not true. Something has to be happening, okay? But now, the concentration, let's just look at this for a while. You have magnesium, ne? It loses electrons. It gives away electrons. It is oxidized. So, like I said, its mass will reduce the mass of the electrode, whereas lead will be increasing. So, in that case, the concentration, okay, let me just do this. Okay, you have magnesium here as a solid. Okay, that's your electrode. There, your anode. Okay, it is in a, no, this is a, yeah, no, this is a, I don't know if I should be drawing this, but whoo. Okay, so we have our beaker there, our second beaker, our salt bridge. Oh my gosh, that salt bridge looks terrible. And you have your anode and your cathode. I'm choosing to put it that side. And then you have your voltmeter reading over there. Okay, and the electrons are going that side. Okay, what else do we have in solution? Okay. I want to redeem myself. Okay. But so on your anode side, you have magnesium. Okay, that's your anode. And then here you have lead. Okay, that's a cathode. Okay, so now, because magnesium is oxidized, okay, electrons keep leaving, you have a whole lot of magnesium 2 plus that is being produced in here. Okay, and as a result, your electrolyte will become thinner. It will lose weight or reduce in mass. But on the other hand, lead, okay, there will be lead ions formed, okay, not as much as your magnesium ions, but lead here will become bigger. Okay, it will increase in mass. Okay, so basically the concentration of magnesium will increase. Okay, so A is not an option. B is also not an option because, like I said, the magnesium ions are increasing. C is an option and D is also an option. So magnesium ions are increasing, the lead ions are decreasing. Okay, C, D. Now what's the difference? There will come a point where you reach equilibrium. Okay, and when you reach equilibrium, at equilibrium, your voltmeter reading, your EMF, actually your E cell will be 0 volts at equilibrium. Okay, and once you reach equilibrium, you know that you'll have like a straight line just to show it's in equilibrium. Okay, so we can't go for D because Iona is just saying for infinity, you have magnesium ions that keep producing. It'll come to a stop, guys. It can't keep producing forever. It's not infinite. It has to come to a point where it is in equilibrium unless something else changes. Okay, so C will be our answer. Okay, I know it took a while, but hey, we're learning here. We don't just want to get to an answer very quickly. And then 1.10. Okay, guys, so here's the thing. You guys are not doing fertilizers. Okay, so the department made provision for a separate question for 1.10. So let me get it quickly. Short break. Okay guys, I'm back. I obtained the correct 1.10. So yeah. Anyway, so now it says the electrolytic cell illustrated below is used to electroplate a nickel rod with copper. Okay, what are they saying here? So you initially have nickel here. Okay, your rod. And you want to electroplate it with copper. So you definitely have copper this side, okay? So copper, once in solution, remember here on the positive terminal, that is where you have your anode. Please do not cram that always on the left-hand side you have an anode and on the right-hand side you have a cathode. Please, don't do that. It's going to end in tears. So you have your anode and you have your cathode this side. Okay, for an electrolytic cell, what actually tells you which side is the anode? The positive side, okay? The anode is positively charged, the cathode is negatively charged, okay? The anode is oxidized, the cathode is reduced, okay? So you have your copper electrolyte, okay? It's a solid, and then in solution, you have your copper 2 plus. Remember, it's oxidized, electrons are donated or gotten rid of. And then, again, on the anode, the actual electrolyte will start losing weight. Okay, it's going to be less. But as the electrons hop over to the cathode side, as this becomes negatively charged, your copper 2 plus ions are going to be attracted to this electrode. Okay, because opposites attract. And as they attract, this nickel will be plated electroplated. Remember electrolysis or electrolytic cells? You get electrical energy converting to chemical energy. So you need electricity to have this happening. Okay, so now you have your copper coming to hug the nickel, coating it basically. Okay, so electroplating, like when you have spoons, that you want golden spoons and not silver spoons, so you coat it with gold. I don't know if it's real gold, but I'm sure you can make a plan. So yeah, that is exactly what's happening here. Now they're saying which one of the following is the correct representation of a suitable electrolyte and the nickel rod that should be used in the above cell to obtain the expected results. Okay, you want nickel that is coated or electroplated with copper. Okay, so your X will actually be indicated by, okay, let's look at A, B, C, D, and E. Your nickel rod is going to be Y. Remember, it is nickel coated with copper. So we're going to look at Y, okay? And Y is for option C and D. Your electrolyte, on the other hand, will be copper sulfate, okay? So sulfate there, that is like your, I don't know if you've heard the term, but your spectator ion, okay? So inside there, we also have sulfates 2 minus, yeah, okay, it's not on top there, but just to write it out nicely, you have sulfates there, okay? So that is like, we don't even put it in the equations when you're writing down the half reactions because it is a spectator ion, the sulfate. But copper, definitely, in your electrolyte, you have copper only, okay? So D has to be the answer. Your electrolyte is copper sulfate and your nickel rod is Y. And with that, guys, we are done. I hope you learned something. Please share the knowledge. Do not keep it to yourself. Share it with your friends, your parents as well, if you want to support or give a reason why you need tutoring. You can show your parents this so that they can see what we do and that we actually know what we're doing. Yeah, and other than that, enjoy the rest of your Saturday morning. It is quite cloudy here in Pretoria. But yeah, that's it from me, and bye.
Well, hello. How are you doing? Welcome to MV Tutors. My name is Figa, and we are doing the prelims, the Gauteng prelims, September 2021 exam. Well, if you wrote this, you just wrote it a few weeks ago, probably just 2 weeks ago, and this is already late because I'm on holiday, believe it or not. I'm on holiday right now, and I just thought I'd record this because, hey, you gotta do what you love during your holiday as well, right? Well, I will tell you this. I'm at a safari. I'm surrounded by, there's a lake right here in front of me. I'm surrounded by hippos. The hippos are just swimming around, and the ostriches are just walking. I see some warthogs there. I can also see some kudu, impalas, springboks. Oh, I see a zebra over there, and you know what, buffaloes over there. It's lovely. I mean, this is Africa. This is the real Africa. Well, without any further ado though, let's just get right into this exam. Right, so this is question number 2, and we are now talking about the letters A to E in the diagram below represents 5 organic compounds. By the way, this is paper 2, question 2, physical science prelim. So this is a chemistry part. This is question 2. All right, so there we are. We see them, there they are. Write down the letter that represents each of the following. Okay, so right now we're looking for a ketone. Okay, so in looking for a ketone, really what we are looking for is something, a functional group of a ketone, remember, is CO. So we're looking for a CO. Does this have COA? No. B, there's no CO there. C, there's a CO over there. That's our functional group. So this is C, and then so C is our answer over there. Okay, and then this one, number 2, a hydrocarbon. Now when we're looking for a hydrocarbon, it's self-explanatory. We're looking for functions, or rather a chain that has C and H only. Okay, an H from hydro and carbon, so C and H only. So let's go. A, C and H only. No, there's a BR there, so that's not what we're looking for. C and H on B, there we go. So B is our answer. Right, here C and H, no, there's an O, so it doesn't count. Here as well, there's an O, doesn't count. What about E? E looks like it's just C and H, so you could have chosen B or E. Both of them are correct. Okay, now let's move on. Let's look for an alkene. Now what is an alkene? An alkene, it has a double bond on the C, so it's got a double bond on the C, so it's CC on a double bond. Let's go. A, is there CC here? Nope. Here, well, nope, doesn't look like it. Here, nope, the double bond is CO. If it was on CC, then that would be an alkene, so that's not our answer. What about here? No double bonds over here for CC. How about here? Now let's look closely. Single bond, single bond, single bond, single bond, single bond, single bonds. Look at this. Now there is a double bond here, if you must know. There's a double bond here because we have CH instead of a CH2. So between these two C's here, right there, we have a double bond. So our answer is therefore E. All right, now let's move on. Write down the IUPAC name for compound A. All right, let's look at A. The first thing you do when you're writing a IUPAC name is that you must name your carbons, right? You must number them rather. So that's 1, that's 2, that's 3, that's 4. Let's make that, which one's gonna be 5? Let's make this one 5, and that's 6. So that's our longest chain. All right, so what does that make it? That makes it, okay, if you look closely, where are we? Over there. So 6 carbons. The number for 6 is hep or hex. It's hex. So we have a hex, and it's all single bond, so it's a hexane. Right, now if you look closely, we got on number 2, we've got a bromo over there, and then on number 3 we have these so it's 1 carbon, so that makes it a methyl, yes. So we've got 2 of them here and here, those are methyls. And then here we've got 2 carbons, so that makes it ethyls. Okay, so how do we do this? Then when it comes to this, we must put it in order. Okay, so what we're going to do then is that we're going to say the first letter between, so we have a bromo, so B comes before a bromo, and a M for methyl, and a E for an ethyl. So the bromo is on 2, so we'll put 2 over there, put a dash. We have a bromo just like that, and then what comes first, an E or or an M? An E comes before an M, so we have an ethyl first. So ethyl is the carbon number 4, so we're gonna have 4 dash ethyl. Okay, and then we're gonna have another dash, then we can put the methyls. The methyls are on carbon number 3, so we'll have 3 and 3 as well. But because it's 2 of them, then it's dimethyl. Oh, I need space. So what I'm gonna do is that I'm just gonna wrap this. I'll put it at the end. Okay, so I'll come back there. So it's dimethyl, and then we'll put the last part. It's a hexane. Hexane. Oh, spelling of hexane. Let's go back. It's a hexane. There we go. So that is the IUPAC name for compound A. Okay, so let's go ahead now. Structural formula of compound D. All right, compound D. There's compound D over there. So let's do the structural formula for it. Okay, let's use blue color. So structural formula, so we'll have a C. Okay, so it's 3H3, so those are our H's, and then we got 2 CH's, so 1 CH2's, and then 2 CH2's. There we go. And then we've got a CH. Okay, so we've got a C and a H, but then we have a OH. So remember, a O is doubly bonded, so those are the 2 bonds. So that's a OH, and then we've got a CH2 again, like that, and then CH3. We've got 3 of these. Okay, now we can go on and put in the H's, because every branch here has an H, just like that. Got an H there, got an H, an H, an H, an H, and another H. There we go. Okay, let's do 2.2.3 now. IUPAC name of the straight chain functional isomer of compound C. Okay, let's check out compound C. Oh, compound C is a ketone, and you must know this, that the functional isomer of a ketone is an aldehyde, right? So with an aldehyde, what we have then, okay, so what I'll do is that I'll just rub this, okay, and then I want us to number the carbon atoms. So that's 1, 2, 3, 4, 5. So we have a pent there. It's a pent. Okay, it's a pent. And then an aldehyde, the suffix there is pentanal. So that's our answer for 2.2.3. Okay, so it's a pentanal. Right, let's move right along. Okay, so 2.3 says compound B is a straight chain compound that undergoes the following exothermic reaction. There we go, thank you. It looks like it has been balanced. So besides being exothermic, what type of reaction is represented above? Okay, so there is this thing that anything where you add oxygen, we call it oxidation. Oxidation, that's it. So that's what's happening here. It's oxidation, adding oxygen. Could also call it combustion if you want. Alright, it's up to you. Both are correct. Now, determine the molecular formula of compound B. Alright, let's see what's happening with compound B. So compound B is this one. It's got an X and a Y there. So we have to balance it up. So let's start with the C. Okay, so what number are we going to put down there? So we're gonna say, okay, this side will look at the other side. How many C atoms do we have? We have 16. So currently we have 2, and then to get to 16 we need to multiply it by 8. So we'll put 8 down here like that. And then let's go to the H then. H, how many H's do we have? We have 18 times 2 of them. Okay, so let's come this side. We already have 2 this side, meaning we need to put 18 of them, just like that. 18. Okay, so we have C8, H18. Cool. Now moving right along, it says the reaction above takes place in a closed container at a constant temperature higher than 100 degrees Celsius at a constant pressure. Thank you very much for telling us that. Now calculate the total volume of gas formed in the container when 50 centimeter cubed of compound B reacts completely with oxygen. So you need to understand what's going on here. Okay, but let's try understand what's going on. They want the total volume of gas. Now if you look at this, we've got CO gas, CO2 gas here, and then we've got H2O gas over here. So then we have to add and consider both of them. Now they tell us that 50 centimeter cube is of this. Now let's go on and look at the molecules. So H18, let's start with the carbon dioxide. Okay, so for every 2 moles of that, let's give each other more space. I'll need that. So for every 2 moles of that, we have carbon dioxide, we have 16 moles of it. And then let's divide both by 2, we'll have 1:8. Okay, let's do the same then with with the water, H2O. So for every 2 moles of this, for the water, we have 18. It's water vapor. So that's 1:9 if I divide both by 2. Okay, how does this help me? It helps me to say then for the total, I'm just gonna cross multiply because I'm looking for the volume for CO2. It's just simply gonna be 8 times 50. Okay, and 8 times 50, that's gonna be 400. And then this side for H2O, it's simply gonna be 8 times no, not 8. I'm not gonna restart this question because I want you to learn that when you make a mistake, you re-evaluate your mistake and try again. So we're just gonna do that. We've re-evaluated. It's not supposed to be 8, but it's supposed to be 9. So it's 9 times 50, which gives us 450. Okay, now all we have to do to get then the total volume, okay, then the total volume, that's gonna be equals to 400 plus 450, which gives us 850. Now because it's the answer, then you put your units, cm cubed. While working out, you don't need to put units, but at the end when you get your answer, always remember to put units. All right, that's it. Well, I hope you understood everything we just did, but in the event that you didn't, please do contact me. I would love to be your tutor. Contact me on www.mvtutors.co.za. Book a free consultation there, or alternatively you can WhatsApp me on 076 312 1107. And if before you contact me, please tell your parent about us first. Show them this video, show them our website, get them involved before contacting us, because remember, at the end of the day, they are the ones who are paying, so they should be involved in the process of tutoring. Other than that, thank you so much and all the best. Welcome to MV Tutors. My name is Figure and I'm on holiday today, but we are still continuing with the prelims, the physical science. This is paper 2 and we are on question number 3 now. So I just want to let you know that I am available to tutor you after this if you so need a tutor. But before you contact me to be your tutor, please speak to your parent about this, show them our videos, and you can contact me after that on my website. Just book a free consultation over there, www.mvtutors.co.za, or alternatively just WhatsApp me on 076 312 1107. Well, hi. So let's continue. Question number 3. Compounds A, B, and C are used to investigate a factor which influences the boiling point of organic compounds. The results of the investigation are given in the table below. So there we go. Okay, all right. Is this a fair investigation? Choose from yes or no. Well, let's check it out. These two are isomers, and you know what? They look like they're positional isomers because it's one, and the functional group is on 1 there, and there it's on 2. But over here, between B and C, these are not. These are chain isomers, meaning they have the same molecular formula, but positional, not the same. Okay, so let's go for no. We're going for no. Give a reason for question number 3.1. Like I said, between A and B, these are positional, even positional isomers. Okay, and then B and C, these are not positional, but they're chain isomers. Okay, so there we go. Now it says fully explain the difference in boiling points of compound B and C. So compound B, the boiling point is definitely higher than compound C. And the reason for that is because if you think of it, this bute has a longer chain. So number 1, it has a longer chain. Okay, longer chain. The butanol. Okay, let me write it like they did. Butan 2-ol. Okay, it has a longer chain, but let's give ourselves more space. It has a longer chain, and because it has a longer chain, it means it's got stronger bonds. Okay, stronger bonds, because it's a straight chain. Okay, a straight chain has stronger bonds than a branched one. Okay, because it's straight. And because it has a stronger bond, that means it must have a higher boiling point, higher boiling point. Man, what am I writing? I'm thinking ahead of my writing. I'm thinking faster than I'm writing. Okay, because it has a higher boiling point, which means more energy is required. Actually, I should have put more energy required first before saying higher boiling point, but you get what's going on there. All right, then it says define the term positional isomer. Well, like I said earlier, a positional isomer. So with a positional isomer, we have a situation where it's an isomer, meaning they have, where am I gonna write this? Let me write it this side. Okay, so positional, so that's, where is it? 3.4. Okay, so they have the same molecular formula, like I said. Same molecular formula, but different positions. Different positions of, say, the functional group. Okay, that's it. All right, so we're gonna do 3.5 now. So it says from compounds A, B, and C, choose the letters that represent each of the following. Positional isomer. Well, we have isomers. We have already spoken about this. That the positional isomers is A and B. Both, as you can see, the functional groups are at 1 and 2. And then in tertiary alcohol, give reason for your answer. So a tertiary alcohol will be C. Now I need to explain this very carefully to you, in case this will be new to you. So the answer, first of all, is C. It's a tertiary alcohol. So there's a difference between a primary, a secondary, and then we have a tertiary alcohol. These are alcohols. So the functional group for a primary is such that the carbon is attached to one other carbon. Okay, so the functional group, that's the functional group for an alcohol, is attached to one other carbon, and then it's H here and H there. Secondary, the functional group, which is COH, is attached to 2 other carbons. That's secondary. And then tertiary is attached to, the functional group is attached to 3 carbons. Okay, so here we have 3 carbons because we have a methyl over here. Okay, so we have a methyl, which means these, if you were to draw this out, you find that there is 3 carbons attached to the functional group of alcohol. That's it. All right, moving on. 3.6, the graph below represents the relationship between vapor pressure and temperature for compound A. Okay, write down the value of X. Okay, so these are boiling points. Let's see. All right, so very often X would be the standard, which is 1 atmosphere. But because here they gave it in kilopascals, 1 atmosphere is equals to 101.3 kilopascals. That's it. Now they say redraw the graph above in the answer book on the same set of axes. Sketch the curve that will be obtained for compound C. Clearly label the curves A and C. Indicate relevant boiling points for compound C on the graph. Okay, so compound A, is that what? Yep, they want compound A is there. The boiling point is 117. Okay, and then C, the boiling point is 82. But now, okay, so let's start with the boiling point. So the boiling point will be down here. That's 82. Okay, or let me just write it like this. 82 over there. That's the boiling point. Okay, that's gonna be our boiling point. Now what we have to decide, will the graph be above or below that of A? Okay, let's go. Let's go look at the table here. This graph, okay, this one is stronger than that. All right, okay, higher boiling point. So it also means the graph actually will be above. Okay, so we'll draw our graph above that. It's gonna be the same as A, but it will be above A. That's C over there. That's the graph of C. Okay, if you want to know the theory of why exactly it's above, well, you know what to do. Contact me. I'd love to be your tutor. You can do so on www.mvtutors.co.za, or alternatively WhatsApp me on 076 312 1107. And please involve your parents first before you contact me, because they are the ones who would be paying for my services. So before you contact me, speak to your parents first and show them our channel and our website, just to give credibility, you know, and then I'm sure they'll be more than happy to assist you in contacting me. Well, that's it from me. Enjoy the rest of your day. Well, welcome to MV Tutors. My name is Figure and I'm your tutor. Well, I'm still on holiday today and I'm recording from my safari destination, but nonetheless we're still doing the prelims, physical science, the chemistry part, which is paper 2, and we are now on question number 4. Okay, so let's get right into it. So question number 4 says the flow diagram below shows various organic reactions using propane. Okay, if you know propane, it's got 3 C's as starting reactant. RT and U represent different organic compounds. Compound T is a carboxylic acid, there it is there, and compound U is a functional isomer, okay, of pentanoic acid. So pentanoic acid, that means pent is 5 C's. Okay, so we start off with 3 C's, we end up with 5 C's. Okay, cool, that's cool. Now it says question number 1, write down the name of the type of reaction represented by reaction number 1. Okay, let's go for red. Reaction 1. Okay, so we're just adding bromo to propane. So adding that, all we can do is just substitute. Where there's an H, we put a Br, and where there's an H again, we put a Br. So it's just substitution. substitution? Well, it's also a halogenation because bromo is a halogen. Could also call it specifically bromination. That's a word because you're specifically using bromo. Okay, and then reaction 2. What's reaction 2? What's happening? We're diluting with this. We've got a hydroxyl here. So even with this, we're getting a propane alcohol, still 3 C's. So it's also substitution. Let's just go very simply, substitution. Okay, so you substituting once again where we have an H with an OH, and that's a functional group of an alcohol. All right, or hydrolysis. It's also hydrolysis because the hydroxyl functional group there because of that. Now it says consider question reaction 1 and reaction 2. Okay, so we're still there. Write down the IUPAC name of compound R. Oh, compound R, we just added bromo, so it's just simply bromopropane. Let's just call it bromopropane. That's it, it's just bromopropane. And then reaction 3 takes place in the presence of a catalyst and heat. Where's reaction 3? Oh, we're over there now. Write down the name or formula of the catalysts. Okay, so this is a bit of theory that you should know. Okay, so one common catalyst that we can use is what we call sulfuric acid. Sulfuric acid. Okay, that's a catalyst. It's not involved in the reaction itself. It doesn't change anything. Okay, but now when it says IUPAC name of compound T now is involved in the reaction. Okay, and let's go get some clues about compound T. They say compound T is a carboxylic acid. So compound T is an acid. Now it's just a matter of what kind of acid is it. Now we know that propane is 3 C's, right? And then we know that compound U, they told us, is an isomer of pentanoic acid. So pent is 5 C's. So in order to get 5 C's from 3 C's, it means we have to add 2 C's, and 2 C's, remember, is what we call ether. Okay, so that, and because it's an acid, then it becomes ethanoic acid. That's why it's ethanoic acid. This acid is now involved in the reaction. That's why we call it an ethanoic acid. But now if you look at the next question, it says structural formula of compound U. We already know that compound U is a functional isomer of pentanoic acid. So we need to, it's got 5 C's and a functional group. So what we're going to do is that, first of all, let me just write the C's, the 5 C's, 1, 2, 3, 4, 5. Okay, and then we need to put a functional group somewhere there. So what I'm gonna do is that I'm gonna put the functional group right there. I'll put the O, and then should I put another O over here? And there we go. And then that's it. This is the functional group over here. The rest is just filling it up with H's. So we got an H there. We've got 2 there. Make sure there's 4 bonds in each one of them. Okay. So 1, 2, 3 there. We've got 2 H atoms there as well here. Got 2 there. That's fine. 1, 2, 3, 4, and then we've got 3 over here. There we go. That's the structural formula. Okay, let's go to the next question now. Okay, let's look at question 4.2 now. It says a laboratory technician wants to prepare but 2-in using but 1-in as starting reagent as shown below. Okay, that's cool. The following chemicals are available in the laboratory. That they are. Select the chemicals required to design this preparation from the list. For each step of preparation, write down the balance equation using structural formulae for all organic compounds. Indicates the chemicals needed in each step. So the important part here is that we are dealing in structural formulae. Okay, that's fine. So we're starting off with this first compound. Fortunately, it's been given to us, so not much thinking is required over there. Well, no thinking at all. You just rewrite what you have been given, and I've got the double bond there. Okay, cool. What have I done? No. Normally I would close this and re-record, but I don't want to do that. When you make a mistake, you should be able to do what I'm doing. Reevaluate your mistake and then try again. There, the double bond is over there. So 1, 2, 3. This one has an H as well. Okay, so what we're gonna do, we'll start off with water, H2O, and then we'll do this in the presence of the H2SO4, okay, as a catalyst. And then what's gonna happen then is that that now is going to become a C, because H2O is coming with an O. Alright, so we're gonna have still but, so we still got 4 of these substitution, so we're just gonna add that functional group over the O there, hydroxyl. Now they don't like you to write OH together. They want you to always do it like this. Put an O and then put an H dash like that. Okay, the rest of these, they have H's. Okay, this one it has a H there, and an H there, an H there, H there. Oh, I've got all these animals roaming here right next to me, and an ostrich is right here. There's 1, 2, 3, 4. So if they come on here and try to bite us or kick us, well, that's that. You've got action happening on your side. Anyway, now that we have this, we're gonna take this compound here. All we have to do is just rewrite it exactly as it is, because we still haven't gotten the but. All we have is that. It's still not but 2-in. Okay, so this one has 2 H's, one more to make it 4 there. Now what we're gonna do, we'll take this compound and then we're still using H2SO4 as a catalyst, but now we are adding heat as well. Okay, so doing this, theoretically what's going to happen is that now we're gonna have 1, 2, 3, 4, And then the functional group or the double bond now is going to be here. Okay, but all the rest is going to be H's. So you must make sure each carbon atom has 4. So 1, 2, 3, 4 over there. 1, 2, 3, 4 over there. And then this one has got 4 all around. But now, this is not all we're gonna get out of this. We're also gonna get water. Okay, so put that H2O plus H2O, because we still have that O there. So it just broke down and it became water, and then there we go. We got our double bond. So we started it off with but 1-ene and it became but 2-ene. That's it, ladies and gentlemen. I hope you understood, but in the event that you didn't, contact me via my website www.mvtutors.co.za. book a free consultation over there, or alternatively you can WhatsApp me on 076 312 1107. Okay, 076 312 1107. That's it. But before you contact me, make sure that you speak to your parent or guardian. Show them our videos, make them like them as well, so that it creates trust and credibility with them, because remember, they are the ones who are going to be paying for my services. Well, I hope you enjoy the rest of your day. Goodbye.
Hello everyone, and welcome back to MV Tutors. I'm Tsolo, and I'll be looking at question 5 with you guys from your paper 2 prelim in the Gauteng region. Okay, so what does it say? Alright, so 5.1 says study the Maxwell-Boltzmann distribution curve for a certain reaction below. So what does the Maxwell-Boltzmann distribution curve actually tell us? Well, it shows us the number of gas particles that are able to react, provided that they have enough activation energy. So in the larger region, where it's white, the particles there do not have enough energy to react. But past R, in the gray region, they have enough kinetic energy to react. And we know that at that point R, that's basically the activation energy required. Okay, if you have a catalyst, well, the activation energy reduces. Okay, so let us see. So P and Q are the labels of the axis. What quantity is represented by P? So basically, on the x-axis, what is that quantity represented by? Okay, so 5.1.1. Basically, P would be the kinetic energy. Okay. Of these particles. And then Q would be the number of particles. Okay. Alrighty. So 5.2. Line R represents the minimum energy required for the reaction to take place. So now, let us write down the term for the underlined phrase. So minimum energy required for reaction to take place, well, basically that is the activation energy. Okay. So before anything can happen, the particles need to at least have more than the activation energy before reaction can occur. Activation energy. Alright, 5.2.1 and then 5.2.2. Well, how will the shaded area on the graph be affected when a catalyst is added? Yes, how will the shaded area on the graph be affected when the catalyst is added? Well, will it increase? Will it decrease? Or will it remain the same? Well, basically, remember the catalyst, what it does, it lowers the activation energy. So if your activation energy is currently here at R, if you add a catalyst while we're expecting the energy to be lowered, right? So you don't need that much energy for a reaction to take place, okay? Thank God for catalysts. So basically now your shaded region will start earlier instead of later, okay? Yeah. Basically, the rates, the rate of reaction. If you want to see how the rate of reaction will be affected when you add a catalyst, your activation energy will be decreased. Okay, so yeah, and what would the answer be? So the shaded area will definitely increase. Okay, hope that makes sense. And then use the collision theory to explain how a catalyst influences the rate of reaction. Okay, so if you recall, let me just remove that. Okay, so if you recall the collision theory, basically, if you have particles that are just roaming about and you want them to react, you want them, first of all, to have enough energy. If they do not have enough energy, guys, as we have seen with the activation energy, if they don't have enough energy, they will not react. So what you want those particles to have enough energy. Once they have enough, specifically kinetic energy, because you want them to move, you want them to collide. So first of all, you want them to have enough kinetic energy to start, moving about. And then the more movement that they have, and when they are orientated in the right way, the more effective collisions you will have. Okay, so first of all, energy. And by having a catalyst, you are actually reducing the activation energy. So you don't have to wait that long for them to have energy, these particles. So these particles are going to have energy at a reduced, instead of taking long to have the energy required, they will take a shorter time to have the energy required. Then they start moving about because it's kinetic energy, and then they start colliding, but not just colliding aimlessly. They will then collide effectively. Okay, and once they collide effectively, you can then have a reaction afterwards. So let us just put all of that in proper words. Okay, so I thought I would write all of that down so that I can save time. But basically, like I explained, when you add a catalyst, you lower the activation energy, as we have seen, to form the activated complex. So what is the activated complex? Well, basically, if you remember your energy, potential energy versus time graph, let's say we have an exothermic reaction. Okay, first of all, this is your activation energy. Okay, and what a catalyst does, it lowers it. Okay, so a catalyst would therefore lower the activation energy, so you don't need that much energy for the reaction to occur. But here at the peak, at the turning point, that is the activated complex. So it is an unstable, temporary position where your reactants are forming into products. So the activated complex is it's very temporary, guys. It doesn't occur over a long time. Quite unstable at that point in time, because that's where your reactants actually form products. Okay, so adding a catalyst, it lowers the activation energy to form the activated complex, okay, where reactants go into products. Then your average kinetic energy of the particle increases. Okay, like I said, you don't need that much energy anymore for your products to form. Okay, so with the catalyst being added, the average kinetic energy of these particles increases. Okay, and then kinetic energy means, the energy for movement. So these particles are now free to move. They move much faster, at a faster rate. They have enough energy to react. And because they have enough energy, you have more effective collisions. Unlike them being slow and not really reacting as fast, then effective collisions wouldn't occur. So here you have enough energy, so the chances of there being effective collisions are quite high, and at the end your reaction rate increases. Okay, so that is how you explain that question, and it is worth 4 marks. So there is quite a bit of writing that you have to do. Okay. Now let us look at question 5.4. Okay, let's go back to my blue pen. Okay, so 5.4, what does it require of us? So the reaction between powdered calcium carbonate and excess hydrochloric acid is used to investigate reaction rate at 25 degrees. Okay, that's the standard temperature. So we have the balanced equation for the reaction. We have calcium carbonate, we have hydrochloric acid, then we have calcium chloride, water, and carbon dioxide. Okay, let us remove this to that side. Now, several experiments are conducted using the same mass of impure calcium carbonate and different initial concentrations of dilute hydrochloric acid. The graph below represents the results obtained. Assume that the impurities do not react. Okay, so you have an impure calcium carbonate. All right, and they show us here on the graph the average rate of production of carbon dioxide versus the initial concentration of hydrochloric acid. Okay, let's just increase the size. Now, for this investigation, write down a controlled variable. Okay, just want to check the marks and the conclusion. Okay, so what is the controlled variable at this point in time? Okay. 5.4.1. So basically, a controlled variable here is something that is really meant to be constant. And what we have read in the introduction is that this reaction actually takes place, or rather, yeah, the temperature here is standard. Okay, so it is at 25 degrees. You have to keep it at 25 degrees. Okay, so a controlled variable, I would then say it is temperature, or one of them is temperature. Okay, the 25 degrees. Another one that I can think of, well, you have, okay, this impure calcium carbonate. The amount of calcium carbonate in that impure compound, well, it is also standard. It is also controlled. So the amount, they will not change. So I could also say that the calcium carbonate, okay, you can use that as well. But it's only 1 mark, so just state one thing and don't waste time. Okay, and then for this investigation, what would be the conclusion, basically? So if you're looking at the y-axis, okay, that is the average rate of production of carbon dioxide. And if we look at the x-axis, that is the concentration of hydrochloric acid. And you can see that basically we have a linear graph there. With increasing concentration, you have increasing rate of production. So what I would conclude there is that the concentration, the higher the concentration, the higher the rate of production or reaction rate. Okay. Okay, so the higher the concentration, the higher the average rate of CO2 production. And what does that tell you? Okay, remember the rate of reaction, what actually affects it. If you have a higher concentration, then your rate of reaction actually increases. So we can then say concentration is directly proportional. Concentration is directly proportional to the rate of reaction. Okay, remember concentration, you also have temperature. When you increase temperature, increase the rate of reaction. We have surface area as well. So you can really comment on that, what actually affects the rate of reaction. In this case, since we have concentration that we have measured, we can then see when you increase the concentration, your rate of reaction actually increases as well. Okay, and now we get to a calculation, guys. Okay, 6 marks. So we are about to work. Prepare yourself. So it says the calcium carbonate in 6 grams of the impure sample reacts completely with 0.03 mole per cubic decimeter of the hydrochloric acid in 26 minutes. So that is the rate, 26 minutes. So use the information in the graph to calculate the percentage purity of the calcium carbonate. Okay, assume that the molar gas volume at 25 degrees is 24,000 cubic centimeters. Okay, so I would convert that cubic centimeters to cubic decimeters. But if you're going to calculate the percentage purity, so percentage purity, basically it is the amount of, let's say in this case, the amount of calcium carbonate, okay, that you have. All right, the actual calcium carbonate that you have over the whole, actually let me put it this way, the mass, let me say the mass of the pure calcium carbonate over the whole sample. Okay, the mass of the sample. Okay, so basically if this sample is 6 grams, maybe let's say you find that calcium carbonate is 4 grams, then you can then calculate the percent purity, and afterwards we multiply it by 100 because we are looking for a percent. Okay, so let's see, we have the mass of the sample already, so that's sorted. Now we need to get the mass of calcium carbonate. So let's see on the table what we can get and also what they have given us, what we can do with it, and let's calculate this percent purity. Okay guys, so they have given us information about carbon dioxide, okay? And what we can do, I think our strategy here is to say, if we can get the number of moles of carbon dioxide, then we can, having reference at our equation here, our reaction equation, if we can have the number of moles of carbon dioxide, we can then go back and get the number of moles for calcium carbonate. Once we have the number of moles of calcium carbonate, we can then get the mass of calcium carbonate. Okay, that is our strategy. Let's see how that will work. So they told us that we have 0.03 mole per cubic decimeters of hydrochloric acid. Now, if we look on the graph, 0.03, let me just note it there. We have 0.03. Okay, it corresponds to 50 cubic centimeters per minute. So that is pretty much our starting point. All right, so let me move a little bit closer. And let's do this. Let's calculate this. So now you have, so for carbon dioxide, okay, you have 50 cubic centimeters per minute. Okay, so maybe I don't really have to change that 24,000 cubic centimeters to cubic decimeters. Okay, let's just hold off a bit. So we have 50 cubic centimeters per minute. And they told us that calcium carbonate in 6 grams of impure sample reacts completely with 0.03 mole per cubic decimeter of hydrochloric acid in 26 minutes. Okay, so I want to remove the minutes. So now I can get what the actual volume of carbon dioxide is. Okay, and if we do that, we have 50 times 26 minutes, and that's 1,300 cubic centimeters. And then they told us that the molar gas volume at 25 degrees, it's 24,000 cubic centimeters. So if they say molar gas volume, Okay, that's actually saying 24,000 cubic centimeters per mole. Okay, it is the molar gas volume, so it is per mole. Please, guys, just note that. Okay. All right. So I'm trying to record it. My son is here. Anyway, we're looking for the number of moles for carbon dioxide. Okay, so what will I have to do? I will have to take the volume of carbon dioxide, which is 1,300 cubic centimeters. And because I'm looking for moles, I'm going to have to swap these around. Okay, so for 1 mole, I have 24,000 cubic centimeters. Okay, so what will cancel? The cubic centimeters are going to cancel, and I'll have my moles, or the number of moles. So let us see, let us do that. So we have 1,300 divided by 24,000, and that is 0,0542. I'm just going to use 542. Okay, so 0,0542. Just make sure I didn't write that incorrectly. 0,0542 mole of carbon dioxide. Okay, so we have the number of mole of carbon dioxide. Now we need to look at our equation and see the ratio of the moles. So I have 1 mole of carbon dioxide there. This equation is balanced, right? Let's check. Yeah, we have 1 calcium, 1 calcium, 2 chlorines, 2 chlorines, 2 hydrogens, and 3 oxygens. So it is balanced. So yeah, we have a 1-to-1 ratio, 1 mole of carbon dioxide, and we have 1 mole of calcium carbonate. So then we know that the number of moles for calcium carbonate is actually equal to 0,0542 mole. Okay, now we need to get the molar mass of calcium carbonate. So let's go check for calcium, for carbon, and for oxygen. 3 oxygen atoms. What are their molar masses? So you get that at the end of your paper. At the periodic table, I don't have the periodic table here. Okay, that sucks. Okay, I don't have the periodic table. Plan B. What is calcium? Let me think. Where can I get it? Let me pause and get the periodic table. Okay, so I found the periodic table. For calcium, we have 40 grams per mole. Okay, as you can see. And then for carbon, we have 12 grams per mole. And for oxygen, we have 16 grams per mole. So there are 3 oxygen atoms, so 16 grams per mole. So if I were to get the total molar mass for calcium carbonate, it would then be, we have 40 plus 12 plus 3 times 16, and that gives us 100. Okay, it's a nice number. So we have 100 grams per mole for your calcium carbonate. Okay, now we can get the mass of calcium carbonate, guys. We are almost there. All right, so yeah, so now the mass for calcium, the pure calcium carbonate, is actually going to be 100 grams per mole. I know you guys normally write it like this. I forgot. So yeah, please excuse the other ones as well. Okay, it's supposed to be grams times mole to the power minus 1. So yes, so now that I have 100 grams per mole, I can multiply by the number of mole that I had, which is 0,0542 mole. So in this case, the mole will cancel, and then I am left with the mass of pure calcium carbonate. Okay, so this 100 I multiplied by 0,0542, 542. And then I have 542, 5,42 grams of calcium carbonate. All right, guys, then we can go back and now we can calculate the percent purity. Okay, so copy that, take it below. Okay, so yeah, so percent purity, it's basically going to be equal to the mass of calcium carbonate, which is 5,42. Wow, there's actually a lot of calcium carbonate in here. And then we have 6 grams, right? The mass of the sample. And then we multiply it by 100. We are expecting like probably 90% or like late 80s. So 5,42 over 6 times 100. 90%. So 90,33%. 90,33%. That is the percent purity of calcium carbonate. So yeah, guys, this concludes question 5. I'll see you guys next time. Please don't forget to share with your fellow matric friends, teachers as well if required, parents if you need motivation for us to tutor you. But yeah, enjoy the rest of your day, morning or evening, depending on when you are watching this. And it's goodbye from me. Hello everyone and welcome to MV Tutors. I'm Tsulu and I'll be looking at question 6 with you guys. Written previously, chemistry, Prelim, Gauteng region. Alright, so it says steam, water and gas form, reacts with hot carbon, alright, at 1,000 degrees according to the following balanced equation. So it's already balanced, we don't need to balance it. Initially 36 grams of steam and a certain amount of carbon were placed in a 2 cubic decimeter sealed container and allowed to react. At equilibrium, it was found that the amount of carbon changed by 0.225 mole. So 6.1, define the term dynamic equilibrium. Okay, guys, so dynamic equilibrium basically is where the rate of the forward reaction is equal to the rate of the reverse reaction. Okay. Yeah, guys, I'm just using arrows so that you know. Forward reaction, the rate, it's important, the rate of the forward reaction is equal to the rate of the reverse reaction. That is dynamic equilibrium, and that is 2 marks. Okay, and then number 2, it says calculate the equilibrium constant for the reaction at 1,000 degrees. 8 marks, guys, we are about to labor here. So remember, the equation for equilibrium constant, well, basically it is the concentration of products, okay, over the concentration of the reactants. And what do we have there? We have that our products, we have hydrogen, okay, and there are 2 moles there to the power 2, and we multiply it by carbon dioxide. Well, there's only 1 mole. We don't really need to write that one. And then we have the steam, okay. Remember, when it comes to calculating the equilibrium constant, you do not involve solids and liquids, only gases and aqueous solutions. Yeah, so please do not make that error of adding solids as well as gases. So in this case, carbon as a solid is not included in the equilibrium constant equation. So yeah, basically we need to get the concentration of hydrogen, of carbon dioxide, and steam. And to do that, I've drawn a table before so that I don't waste time, and then we can fill it in. Okay, now where's this table? Please don't tell me the table disappeared. Okay, here it is. Let me just bring it a bit up. So I will be using the rice method. It's actually going to be ricey. But yeah, you'll see now in a moment what I mean. So, here it's actually supposed to indicate a double line just to show separation of reactants and products. So our reactants, like we said, we have water, or rather steam, and our products, we have hydrogen as well as carbon dioxide, and all of them are in gas form. Okay, so rice. Okay, or rather, let me do this. So should have made this a bit bigger. So all of these will be in moles. So the rice part. Okay. And then why I said ricey is because now we need to have it in concentration form. Okay, so rice, what does that stand for? Basically, that is the ratio of moles that we have. Okay, so for steam, we have 2 moles. For hydrogen, we have 2 moles, and carbon dioxide, it's only 1 mole. And initially, so when this reaction is about to start, initially, we need to get the amount of moles that we have, okay? So we already know that initially there aren't any products, but we need to calculate initially what we had for steam. And they told us we have 36 grams of steam, okay? And now we need to go get the molar mass of steam. So we have 2 atoms of hydrogen. And if you look at your periodic table, actually hydrogen is just 1. So we have 2 grams per mole. And then for oxygen, we have 16 grams per mole. You can check that on the periodic table. Yeah, it is. So in total, we actually have, 18 grams per mole of the steam. Okay, so I would like to have the number of moles for steam. Okay, so if I want to have that, I'm going to take 1 mole per the 18 grams, just swapping it around. Okay, I don't know why I keep writing it this way, I keep forgetting. So it's actually 18 grams per mole. Okay, so 1 mole, 18 grams, and I'm going to multiply that by 36 grams because I would like to get rid of the... Sorry about that. Oh my gosh. So I would like to get the number of moles for steam and actually remove the number of grams. So 36 divided by 18, that would give me 2. So the grams cancel out and I'm left with moles. So initially, I had 2 moles of the steam, but hydrogen and carbon dioxide were not formed yet. So that will be 0. And now let's look at the change. Have they mentioned anything about change? Yes, they did say at equilibrium, it was found that the amount of carbon changed by 0.225 mole. And this is where now the ratio come in. The ratios come in, okay? We have 2 moles for hydrogen, 2 moles for steam, and 1 mole of carbon dioxide. So if carbon changed by 0.225 mole, carbon dioxide will also change by 0.225 mole because they have a 1-to-1 ratio. But for the others, where they have 2 moles, we're going to double that. So 0.225, that should be 0.45. Let's just make sure. I have 0.225 times 2. Yes, it's 0.45. And then now to get at equilibrium the number of moles. So here, remember, the reactants are busy reducing, or rather being used up. I think that's the right word. The reactants are being used up while the products are forming. So if we take 2 and subtract 0.45, we're going to get 1.55. Okay, that's the change. And then 0 plus 0.45 will remain 0.45, and 0 plus 0.225. Ooh, gosh, speaking can be a challenge sometimes. Okay, so at equilibrium, we have the number of moles, guys. Now we need to get the concentration because we need that to calculate our equilibrium constant. So now with steam, okay, if we're going to get the concentration, remember concentration, number of moles over volume. So if I'm going to get the concentration of steam, I know that the number of moles I have at equilibrium is 1.55 mole. And they told us all of this. The steam initially was placed in a 2 cubic decimeter sealed container. So 2 cubic decimeters. Okay, so if I were to get the concentration of steam, it's going to be 1,55 divided by 2, which is 0,775 mole per cubic decimeter. So 0,775. Okay, and then what will it be then for sorry, what will the values then be for hydrogen and carbon dioxide? Okay, so now we need to we have the number of mole, all right, and yeah, remember all of this is taking place in a 2 cubic decimeter sealed container. So you're going to do the same thing as we have done for the steam. So you're going to take the number of mole that you have and divide it by 2. Okay, so 0,45 divided by 2, that should be 0,225. Okay, and then 0,225 divided by 2, that's 0,1125. So we have our concentrations, guys. Wasn't this nice? Well, it's nice if you know what you're doing. But yeah, we now have our concentrations and we can then substitute it in this formula over here. So I am going to copy and paste it below and then we'll fill it up. Okay, so I'm just going to write on the side. For hydrogen, we have 0,225 to the power 2. For carbon dioxide, we have 0,1125. And then for the steam, we have 0,775 squared. Yeah, guys, this was laborious, but it is worth the 8 marks. So 0,225 squared times 0,1125 all over 0,775 squared. I feel like this calculator is going to show me flames with the answer as expected. So I have 0,0095. Yes, it doesn't have units. I was about to say, what are the units? It doesn't have units, guys. It's a constant, so equilibrium constant. If you wanted to, you could have taken this comma, so 1, 2, 3. So it can be 9,48 times 10 to the power minus 3. And we have completed this 8-mark question. Fabulous. Okay, now we get to 6.3. Okay, so the graph shows how the rates of the forward and the reverse reactions change with time. So the solid line is the forward reaction and the dotted line is the reverse reaction. Okay, so with the forward reaction, we see that we actually, let me just make notes here. Okay, I'm going to pause, put all the notes so that we can discuss afterwards. Okay, guys, so initially, if you look at the forward reactions, your reactants are at their maximum, right? Because you want to form products. But the products start at 0, okay? Just like we saw on that table we drew. So products then start increasing over time while the reactants decrease. Okay, so reactants are forming into products, okay? And then you reach a state of equilibrium. So where the lines are actually parallel and just flat, that's where equilibrium is reached. And then something happens. At T2, you actually increase temperature, okay? And when you increase temperature, the reactants actually just shoot up immediately. So there's a sharp increase. And what happens then, according to Le Chatelier, if the reactants were increased, what do you need to do to balance it? You need to increase the products. So eventually, the reactants start going down, okay, and the products start increasing, just so that a new equilibrium can be reached. And between T2 and T3, of course, towards the end, towards T3, there's another equilibrium point there. And then, guys, at a point where your forward reaction line and your reverse reaction line, where they're actually parallel, no matter what change goes there, you see there's an increase. Both the reactants and products have increased at the same rate or the same way. So in that case, then you have a catalyst at that point, okay? When they are parallel to each other and move the same way, it's because there is a catalyst. Okay, so let us answer questions. Hopefully we will flow after all of that. Now it says, give a reason why the rate of the forward reaction decreases between T0 and T1. Well, basically, the reactants are being used up. Okay? And in this case, that is the steam. Remember, we had steam there at the beginning, so it's being used up. And then what change was made to the equilibrium mixture at T3? Okay, so like we said, guys, we discussed it. A catalyst was added. I just want to see. It's 1 mark. So yeah, they added a catalyst. Okay, and then 6.3.3. At time 2, the temperature of the system is increased. Yes, that's true. Oh, please don't mind the bottom arrow here. I was just trying to indicate that at this point, the temperature is increased. Okay. Now 6.3.3 says, is the forward reaction exothermic or endothermic? Okay, guys. So if you increase temperature on your reactant side, how many marks is this? 1 mark. Okay, so if you increase the temperature and your reactants are actually increasing, okay, then you would then say it is endothermic. Okay, if you decrease your temperature and your products increased, then you would say it's exothermic. So in this case, we have an endothermic reaction. Okay. All right, and then 6.3.4 it says, refer to Le Chatelier's principle to explain the answer in question 6.3.3. Okay, I'm going to try to explain it first in words and try to summarize it in writing. So when you increase temperature, do you see that both, let me just make notes there. If you increase temperature, you see that both the forward reaction and the reverse reaction, they increase. Okay, but the forward reaction increases more. Okay, and that's why we could formulate that it is actually an endothermic reaction on the reactant side. Okay, yes, the forward reaction is endothermic. So now, but to apply Le Chatelier, okay, if you have an endothermic reaction and the temperature is increased, your reactants will increase, or the rate at which the reactants react, it will increase. So to apply Le Chatelier's principle, we need to find a balance, okay? So now what it does, Le Chatelier, what he proposes is that we increase the products, okay? And as you increase the products, your reactants will start decreasing. And that's why we see it there. The reactants will decrease while the products increase so that you can reach a new equilibrium. Okay, so now to put that in words. So initially, like we saw here, the forward reaction was favored. And as the forward reaction was favored, we see that the increase in temperature the increase in temperature favors it favors the reactants. Okay, and then for a new equilibrium to be reached, like I said, the products will then have to increase and the reactants decrease. Okay, yes. So what I mean by the forward reaction favored, so it means on the product side. I hope I'm not confusing you guys. Yeah. Basically, for a new equilibrium to be reached, the products need to be increased while the reactants reduce, and then you can reach a new equilibrium. Okay, so the only thing to take out of this, if you remember everything I've said, while you increase the temperature, the reactants increase, and to balance it out, according to Le Chatelier, the products have to be increased. Okay, hence the forward reaction is favored. Okay, so increase in temperature, the immediate increase in temperature initially favors the reactants, but as time goes by, the forward reaction will be favored. And we are done, guys, with question 6. I know sometimes it's a challenge to many, but I hope you understood, and I hope I didn't lose you guys anyway. But that is it from me. Please don't forget to like our videos and subscribe to our channel. Thank you. Hello everyone, and welcome to MV Tutors. I'm Tseluro, and I'll be looking at question 6 with you guys. Written previously, chemistry, Prelim, Gauteng region. Alright, so it says steam, water and gas form, reacts with hot carbon, alright, at 1,000 degrees according to the following balanced equation. So it's already balanced, we don't need to balance it. Initially, 36 grams of steam and a certain amount of carbon were placed in a 2 cubic decimeter sealed container and allowed to react. At equilibrium, it was found that the amount of carbon changed by 0.225 mole. So 6.1, define the term dynamic equilibrium. Okay, guys, so dynamic equilibrium basically is where the rate of the forward reaction is equal to the rate of the reverse reaction. Okay. Yeah, guys, I'm just using arrows so that you know. Forward reaction, the rate, it's important, the rate of the forward reaction is equal to the rate of the reverse reaction. That is dynamic equilibrium, and that is 2 marks. Okay, and then number 2, it says calculate the equilibrium constant for the reaction at 1,000 degrees. 8 marks, guys. We are about to labor here. So remember, the equation for equilibrium constant, well, basically it is the concentration of products, okay, over the concentration of the reactants. And what do we have there? We have that our products, we have hydrogen, okay, and there are 2 moles there to the power 2, and we multiply it by carbon dioxide. Well, there's only 1 mole. We don't really need to write that one. And then we have the steam, okay. Remember, when it comes to calculating the equilibrium constant, you do not involve solids and liquids, only gases and aqueous solutions. So please do not make that error of adding solids as well as gases. So in this case, carbon as a solid is not included in the equilibrium constant equation. So yeah, basically we need to get the concentration of hydrogen, of carbon dioxide, and steam. And to do that, I've drawn a table before so that I don't waste time, and then we can fill it in. Okay, now where's this table? Please don't tell me the table disappeared. Okay, here it is. Let me just bring it a bit up. So I will be using the rice method. It's actually going to be ricey. But yeah, you'll see now in a moment what I mean. So, here it's actually supposed to indicate a double line just to show a separation of reactants and products. So our reactants, like we said, we have water, or rather steam, And our products, we have hydrogen as well as carbon dioxide, and all of them are in gas form. Okay, so rice. Okay, or rather, let me do this. So should have made this a bit bigger. So all of these will be in moles. So the rice part. Okay. And then why I said ricey is because now we need to have it in concentration form. Okay, so rice, what does that stand for? Basically, that is the ratio of moles that we have. Okay, so for steam, we have 2 moles. For hydrogen, we have 2 moles, and carbon dioxide, it's only 1 mole. And initially, so when this reaction is about to start, initially, we need to get the amount of moles that we have, okay? So we already know that initially there aren't any products, but we need to calculate initially what we had for steam. And they told us we have 36 grams of steam, okay? And now we need to go get the molar mass of steam. So we have 2 atoms of hydrogen. And if you look at your periodic table, actually hydrogen is just 1. So we have 2 grams per mole. And then for oxygen, we have 16 grams per mole. You can check that on the periodic table. Yeah, it is. So in total, we actually have, 18 grams per mole of the steam. Okay, so I would like to have the number of moles for steam. Okay, so if I want to have that, I'm going to take 1 mole per the 18 grams, just swapping it around. Okay, I don't know why I keep writing it this way, I keep forgetting. So it's actually 18 grams per mole. Okay, so 1 mole, 18 grams, and I'm going to multiply that by 36 grams because I would like to get rid of the... Sorry about that. Oh my gosh. So I would like to get the number of moles for steam and actually remove the number of grams. So 36 divided by 18, that would give me 2. So the grams cancel out and I'm left with moles. So initially, I had 2 moles of the steam, but hydrogen and carbon dioxide were not formed yet. So that will be 0. And now let's look at the change. Have they mentioned anything about change? Yes, they did say at equilibrium, it was found that the amount of carbon changed by 0.225 mole. And this is where now the ratio come in. The ratios come in, okay? We have 2 moles for hydrogen, 2 moles for steam, and 1 mole of carbon dioxide. So if carbon changed by 0.225 mole, carbon dioxide will also change by 0.225 mole because they have a 1-to-1 ratio. But for the others, where they have 2 moles, we're going to double that. So 0.225, that should be 0.45. Let's just make sure. I have 0.225 times 2. Yes, it's 0.45. And then now to get at equilibrium the number of moles. So here, remember, the reactants are busy reducing, or rather being used up. I think that's the right word. The reactants are being used up while the products are forming. So if we take 2 and subtract 0.45, we're going to get 1.55. Okay, that's the change. And then 0 plus 0.45 will remain 0.45, and 0 plus 0.225. Ooh, gosh, speaking can be a challenge sometimes. Okay, so at equilibrium, we have the number of moles, guys. Now we need to get the concentration because we need that to calculate our equilibrium constant. So now with steam, okay, if we're going to get the concentration, remember concentration, number of moles over volume. So if I'm going to get the concentration of steam, I know that the number of moles I have at equilibrium is 1.55 mole. And they told us all of this The steam initially was placed in a 2 cubic decimeter sealed container. So 2 cubic decimeters. Okay, so if I were to get the concentration of steam, it's going to be 1,55 divided by 2, which is 0,775 mole per cubic decimeter. So 0,775. Okay, and then what will it be then for sorry, what will the values then be for hydrogen and carbon dioxide? Okay, so now we need to get, we have the number of mole, all right, and yeah, remember all of this is taking place in a 2 cubic decimeter sealed container. So you're going to do the same thing as we have done for the steam. So you're going to take the number of mole that you have and divide it by 2. Okay, so 0,45 divided by 2, that should be 0,225. Okay, and then 0,225 divided by 2, that's 0,1125. So we have our concentrations, guys. Wasn't this nice? Well, it's nice if you know what you're doing. But yeah, we now have our concentrations and we can then substitute it in this formula over here. So I am going to copy and paste it below and then we'll fill it up. Okay, so I'm just going to write on the side. For hydrogen, we have 0,225 to the power 2. For carbon dioxide, we have 0,1125. And then for the steam, we have 0,775 squared. Yeah, guys, this was laborious, but it is worth the 8 marks. So 0,225 squared times 0,1125 all over 0,775 squared. I feel like this calculator is going to show me flames with the answer as expected. So I have 0,0095. Yes, it doesn't have units. I was about to say, what are the units? It doesn't have units, guys. It's a constant, so equilibrium constant. If you wanted to, you could have taken this comma, so 1, 2, 3. So it can be 9,48 times 10 to the power minus 3. And we have completed this 8-mark question. Fabulous. Okay, now we get to 6.3. Okay, so the graph shows how the rates of the forward and the reverse reactions change with time. So the solid line is the forward reaction and the dotted line is the reverse reaction. Okay, so with the forward reaction, we see that we actually, let me just make notes here. Okay, I'm going to pause, put all the notes so that we can discuss afterwards. Okay, guys, so initially, if you look at the forward reactions, your reactants are at their maximum, right? Because you want to form products. But the products start at 0, okay? Just like we saw on that table we drew. So products then start increasing over time while the reactants decrease. Okay, so reactants are forming into products, okay? And then you reach a state of equilibrium. So where the lines are actually parallel and just flat, that's where equilibrium is reached. And then something happens. At T2, you actually increase temperature, okay? And when you increase temperature, the reactants actually just shoot up immediately. So there's a sharp increase. And what happens then, according to Le Chatelier, if the reactants were increased, what do you need to do to balance it? You need to increase the products. So eventually, the reactants start going down, okay, and the products start increasing, just so that a new equilibrium can be reached. And between T2 and T3, of course, towards the end, towards T3, there's another equilibrium point there. And then, guys, at a point where your forward reaction line and your reverse reaction line, where they're actually parallel, no matter what change goes there, you see there's an increase. Both the reactants and products have increased at the same rate or the same way. So in that case, then you have a catalyst at that point, okay? When they are parallel to each other and move the same way, it's because there is a catalyst, okay? So let us answer questions. Hopefully we will flow after all of that. Now it says, give a reason why the rate of the forward reaction decreases between T0 and T1. Well, basically, the reactants are being used up. Okay? And in this case, that is the steam. Remember, we had steam there at the beginning, so it's being used up. And then what change was made to the equilibrium mixture at T3? Okay, so like we said, guys, we discussed it. A catalyst was added. I just want to see. It's 1 mark. So yeah, they added a catalyst. Okay, and then 6.3.3. At time 2, the temperature of the system is increased. Yes, that's true. Oh, please don't mind the bottom arrow here. I was just trying to indicate that at this point, the temperature is increased. Okay. Now 6.3.3 says, is the forward reaction exothermic or endothermic? Okay, guys. So if you increase temperature on your reactant side, yeah, how many marks is this? 1 mark. Okay. So if you increase the temperature and your reactants are actually increasing, okay, then you would then say it is endothermic. Okay, if you decrease your temperature and your products increased, then you would say it's exothermic. So in this case, we have an endothermic reaction. Okay. All right, and then 6.3.4 it says, refer to Le Chatelier's principle to explain the answer in question 6.3.3. Okay, I'm going to try to explain it first in words and try to summarize it in writing. So when you increase temperature, do you see that both, let me just make notes there. If you increase temperature, you see that both the forward reaction and the reverse reaction, they increase. Okay, but the forward reaction increases more. Okay, and that's why we could formulate that it is actually an endothermic reaction on the reactant side. Okay, yes, the forward reaction is endothermic. So now, but to apply Le Chatelier, okay, if you have an endothermic reaction and the temperature is increased, your reactants will increase, or the rate at which the reactants react, it will increase. So to apply Le Chatelier's principle, we need to find a balance, okay? So now what it does, Le Chatelier, what he proposes is that we increase the products, okay? And as you increase the products, your reactants will start decreasing. And that's why we see it there. The reactants will decrease while the products increase so that you can reach a new equilibrium. Okay, so now to put that in words. So initially, like we saw here, the forward reaction was favored. And as the forward reaction was favored, we see that the increase in temperature the increase in temperature favors It favors the reactants. Okay, and then for a new equilibrium to be reached, like I said, the products will then have to increase and the reactants decrease. Okay, yes. So what I mean by the forward reaction favored, so it means on the product side. I hope I'm not confusing you guys. Yeah, basically for a new equilibrium to be reached, the products need to be increased while the reactants reduce, and then you can reach a new equilibrium. Okay, so the only thing to take out of this, if you remember everything I've said, while you increase the temperature, the reactants increase, and to balance it out according to Le Chatelier, the products have to be increased. Okay, hence the forward reaction is favored. Okay, so increase in temperature, the immediate increase in temperature initially favors the reactants, but as time goes by, the forward reaction will be favored. And we are done, guys, with question 6. I know sometimes it's a challenge to many, but I hope you understood, and I hope I didn't lose you guys anyway. But that is it from me. Please don't forget to like our videos and subscribe to our channel. Thank you.
Well, welcome to MV Tutors. My name is Figa and I'm your tutor today. Okay, so I'm still in the safari and just having a nice time out here with animals, but we're still doing the prelims, physical science, paper 2. This is chemistry, and we are now on question number 7. Well, if you will need a session after this, then please, I cannot state this enough, please show this video to your parents. Show your parents our website, just to create credibility. But whatever you do, consult your parents before consulting us to be your tutors. Okay, but I will give you all the details at the end of how to get a hold of me. Otherwise, you'll find it in the description of this video if you don't finish it. Right, let's get right into it. Question number 7. It says 2 beakers, A and B, containing strong bases. So that's A, that's B, cool. Beaker A, 500 centimeter cubed. Okay, it's labeled. Of barium hydroxide. Okay, thank you. Of unknown concentration X. All right, we don't know the concentration. Probably they'll want us to solve for it. Whenever you see an X, they probably want you to solve for an X. Okay, beaker B, 400. Okay, we see it. Of potassium hydroxide of concentration 0.1. Thank you so much. It's given. Okay, I guess that's all we need to know. Now it says define a base according to the Arrhenius theory. Okay, now you should know this, but I'm just going to write it to make sure that you know what it is. Now, a base is just something. A base, it actually forms what do you call these things? Look at them. OH. These OH ions, we call them hydroxide ions. Hydroxide ions, okay, in water. That's it. So a base ionizes to form hydroxide ions. That's it. Okay, now it says 7.2, calculate the number of moles of hydroxide ions in beaker B. Now, 7.2. Now we know from your formula sheet, you get this from your formula sheet, that concentration is actually equals to number of moles of a volume, right? And here they want us to calculate the number of moles. So Number of moles then will be equals to concentration times the volume. Okay, concentration, they said at beaker B, concentration we've been given is 0.1. So there we go, 0.1 times the volume we know is 400. But we need to convert this 400 centimeter cube to decimeter cube, because look at this. This concentration is in decimeter cubed as well. So that's why we have to convert it. So converting centimeter to decimeter, we divide by 1000. Okay, so what I'd like to do right now at this point is just bring out a calculator, put it exactly as it is. So it's 0.1 times 400 divided by 1000, like that. Okay, we want it 0.04. Thank you so much. So it's equals to 0.04 mole. That's it. Okay, let's do question 7.3 now. And it says the contents of beaker A and B are added together in beaker C. Okay, I see the arrows also showing that. The solution in beaker C has a pH of 13. Thank you so much. Assume that the volumes are additive and that the temperature of the solution is 25 degrees Celsius. Right, now calculate the concentration X of barium hydroxide in beaker A. So there we are, we did with beaker A. So I want us to do this systematically. So what I mean is that, okay, let's start here. We need to be able to read this slowly. First of all, we are solving concentration. Okay, so what's the formula for concentration? It's C equals to number of moles divided by volume, right, of barium hydroxide. So now what do we know about barium hydroxide? So it's BOH2. Okay, now that you get Ba ions plus the hydroxide ions, right? But check this out. Check this out. You are going to have 2 moles of that. Okay, and because it's 2 here, so also here it's gonna be 2 plus. This is balanced now. We've got 2. It's a balanced equation. It must be balanced. You've got 1 Ba, 1 Ba, 2 O's. We got 2 O's this side, 2 H's. Got 2 H's there. It's balanced. So now what we're going to do is that we're going to solve the number of moles of OH first, and then we're going to use those to number of moles to solve the concentration, because right now we have the volume, which is don't have the number of moles. So in order to solve the number of moles of that, let's start with this pH here. We've got a clue, a pH of 13. So we need to solve the pOH and get the concentration of the OH ions, and then we'll use them to get the moles of the hydroxide ions. So let's do this. Now we know that pH plus pOH is equals to 14, okay, by definition. So we have been told then that the pH is 13 and we want the pOH, right? That's 14. So to get the pOH, it's just gonna be 14 minus 13, which is equals to 1. We also know that to solve pOH, that's equals to the minus log of the concentration of the OH, okay? And then to get the concentration of the OH, we know there's an imaginary 10 there, so it's 10 minus pOH, right? And now we know that POH is 1, we solved it there, then it means that our final answer, our concentration for OH ions is 0.1. 10 to the power minus 1 is 0.1 mole per decimeter cubed. That's for OH ions, concentration of OH. Now we're gonna come back and say the concentration of the concentration is equals to the number of moles of a volume. We want the number of moles, so that's going to be equals to CV, okay, and the concentration is 0.1 times what's the volume. Remember, we are on beaker C, so the volume of beaker C is 500 plus 400, which is 900, because you're adding A and B together. So then we'll come back, put 900 over there. To convert it, divide by 1,000. All right, let's get a calculator real quick. So on our calculator, then we'll have 0.1 times 900 divided by 1,000. That's going to be equals to 0.09 moles. Okay, so these are the number of moles on beaker C, right? We are really interested in the number of moles in beaker A. Okay, so what we're gonna do then is that we're gonna say, to get the number of moles in beaker A, we're gonna have to say number of moles in beaker C minus the number of moles in beaker B, okay, so that we get the number of moles in beaker A. So number of moles in beaker C is 0.09. Number of moles in beaker B, we solved them earlier. There they are, it's 0.04. Okay, so we can go back here. We'll put that 0.04. Okay, 0.09 minus 0.04, 0.05 moles. Okay, ladies and gentlemen, I need you to understand what these number of moles are for. These number of moles in beaker A are for the hydroxide ions. Okay, so when we come here, we just solve the number of moles of hydroxide ions, and you can see that the ratio is 2:1. We are interested in the number of moles of beryllium hydroxide, not of hydroxide alone. So okay, let me just continue this side. So we are then saying that we want beryllium hydroxide is 2 OH ions. Okay, so here we are saying the ratio is 1:2, and if the ratio is 1:2, we just solved that this one is 0.05. we need the number of moles. Let me put X rather, so that you know we're solving for X. Okay, so cross multiplying, okay, like that. So it's 2x, and then 1 times that is 0.05. To get x, that's gonna be 0.05 divided by 2. Well, I know it's 0.025. Let's just put it mole. Okay, so this is the number of moles of beryllium hydroxide. Now that we have the number of moles of beryllium hydroxide, we can then use them to solve the concentration, because now we are here. Concentration is number of moles divided by volume. Okay, number of moles is 0.025 divided by the volume in A. What's the volume in beaker A? It's 500. So it's divided by, here we are, it's divided by 500, and to convert it we need to divide it by a further 1000. Okay, so let's get our calculator. Here we go. First of all, with our calculator, let's just check 0.05 divided by 2, 0.025, so we are cool there. Now let's put this one. Remember, on top we have 0.025, and at the bottom do it like this, because if you just put it in the calculator exactly as it is here, it might cause problems. So here I'll put 500 divided by 1000. Okay, and then I get 0.05. Okay, that's our answer. I just want to show you what happens if I had said 0.025 divided by 500 divided by 1000. We would get the wrong answer. Look at that. Yeah, so our correct one is 0.05 mole per decimeter cube. That's it. That's our concentration. That's our final answer right there. Okay, let's move on then. Let's go to the next question. It says, where were we? We just calculated the concentration. Okay, the solution in beaker C is titrated with ethanoic acid. It was found that 15 centimeter cube of the solution neutralizes 30 centimeter cube of the acid. The balanced equation for the reaction is that. Thank you. You know, I just remembered something here that we forgot in question 7.2. Okay, even though we did this in 7.2, remember it says calculate the number of moles of hydroxide ions in beaker B. Beaker B has potassium and OH, so that means that potassium hydroxide, that is potassium, okay, plus OH ions, and the ratio is 1:1. Now when we were calculating here, that was the concentration and that was the volume, but you know, we need to keep this in mind as well. It doesn't always work out this well. You know, we need to have it in mind, because remember, this concentration and that volume, yes, they deal with the whole compound, but this is the equation, just like we use this equation here where we found that it's 2:1. Here it was 1:1. Okay, so that was for 7.2. Anyway, let's move on. Now it says, is ethanoic acid a weak or a strong acid? Well, you should know this from theory. It's a weak acid. It's weak. And why is it weak? It does not dissociate completely. If it was a strong, it dissociates completely by definition. Okay, then the last question here says calculate the concentration of ethanoic acid. All right, so we need a different formula here, and the formula that we're going to use 7.2 3.3 is this one that says, remember C is equals to NV. That means N is equals to CV. So we can say then concentration of the acid times the volume of the acid is equals to the number of moles of the acid, and then we're just gonna divide that by the base. Okay, divide by the number of moles of the base. Okay, let's go on and fill these up now. Concentration of acid, that's what we're looking for. Volume of the acid. Now what is the volume of the acid? Let's go back and read here. It was found that 50 centimeter cube of a solution neutralizes 30 centimeter cube of acid. So acid is 30. Okay, so we have a 30 there. Concentration of the base. What is the concentration of the base? Didn't we just solve it? Okay, which beaker are we talking about here? The solution in beaker C is titrated with, so we're in beaker C. So the concentration of the base in beaker C is what we just solved now. Where is it? 0.0. No, that's beaker A. I want beaker C. There it is. Was it 0.09 concentration? No, it was 0.1 there. Okay, 0.1. Yep, 0.1. This one where we solved it down here. So that's the concentration of beaker A, 0.1, and then the volume of the base one is, it was found that 15. It's 15. Okay, so that's equals to number of moles. If we look at the balance equation, everything is 1:1, so it's just 1/1. Now we're looking for CA. We'll just do some gymnastics. Okay, we're just gonna do some mathematical gymnastics. That's what they call them, right? Mathematical gymnastics. Okay, sorry, I have some ostriches. They're eating right in front of me, so you know sometimes they can be a distraction. Anyway, I hope they don't come here. Okay, so let's just do mathematical gymnastics. It's gonna be CA is equals to 1. This is the 1, and then if I take this to the other side, it's gonna be 0.1 times 15 divided by 30. All right, let's bring out our calculator. So that is going to be 0.1 times 15 divided by 30, and we get 0.05. Where's my back button? Okay, 0.05. Wow, this 0.05 is a popular number today. But anyway, that's it. 0.05 moles per decimeter cube. Now, in the event that there was something that you didn't understand here, or that you need tutoring on, don't hesitate. Contact me. Visit my website, book a free consultation there, or WhatsApp me. I've already given you my number, but it's also in the description of this video. Well, that's it from me. All the best.
Hello everyone and welcome to MV Tutors. I'm Tsilo and I'll be looking at question 8 with you guys. Okay, let us read. So, a galvanic cell a galvanic cell at standard conditions is represented by the cell notation below. X and Y are unknown electrons. Okay, so before we even get far, I just want us to analyze what is actually happening here. what they are showing us or what they are telling us. Okay, so I know that X, first and foremost, is my anode. Okay, the electrolyte called the anode. Okay, and I know this double line here represents the salt bridge. Okay, and then Y would be my cathode. Okay, and we know that at the anode, that is where oxidation occurs. Whether you have a galvanic cell or you have electrolytic cell, whether you have an electrolytic cell, that is where oxidation occurs, at the anode. So this anode of ours underwent oxidation. Okay, so it was oxidized. Okay, and as it was oxidized, it means it lost electrons. Hence, you now have this zinc 2 plus. And then on the Y, you have your cathode. Okay, so your cathode, that is where reduction occurs. Okay, and where reduction occurs, so we see here, reduction, that is where it occurs, and you are gaining electrons. So yeah, basically what you see here, because you are gaining electrons on the cathode side, where reduction occurs, you can see that you have your iron 3 plus going all the way to iron 2 plus. It has gained an electron, right? Okay, so I hope you saw that and you understand that. And now let us answer the questions. All right. So 8.1.1, write down the name or formula of electrode X. Okay, guys, so if you had X and then after oxidation you have zinc 2 plus, then you know that your electrode is zinc. Okay, so you have zinc, the solid zinc. Okay, just say zinc. And then 8.1.2, electrode Y. So we know we have that solution there of iron 3 plus, okay, and after the electrons are given or when the electrons are headed to the cathode side, we know that we have iron 3 plus going to iron 2 plus. Your cathode in most cases in your galvanic cell that you would use would be platinum. Okay, so I would say PT, right, or just plainly platinum. Okay, and then 8.1.3, the oxidizing agent. Okay, so let's look at this. Let's look at this. Ooh, English. Okay, so where oxidation occurs, which is there at the zinc, we have your reducing agent. Okay, where reduction occurs, which is at the cathode, you have your oxidizing agent. So if we're going to write down the formula of the oxidizing agent, yeah, we're looking really at iron there. Okay, yes, oxidizing agent. So you have iron 3 plus. Yeah, what's another way of writing this? I would say iron 3. Yeah, that's what I think. Okay, so yeah, whenever you have an iron, please just put there AQ, aqueous solutions. Okay, so now let us see. Write down, so for 8.2.1, let me just also go a bit up. Write down one function of electrode Y. So what is the function of platinum in this case? Well, basically, if you look at your galvanic cell, okay, if we were to draw it out quickly, how many marks is this? 1 mark. Okay, so the long and short of it, or rather the short of it, is it allows electrons to flow through. So it's like a conductor. Let me not go far. Let me not go that far. So it is a conductor, okay, which means it allows the flow of current, okay, you know, through electrons basically. Yeah, let me not say too much, but it allows the flow of the current. Okay, so the electrons are going through, current is going through, it is a conductor. If you do draw out a galvanic cell, you know you have one beaker where you have your anode, okay, and you have a wire with a battery, okay. Then on the other side you have your cathode, the beaker there, and then the salt bridge. Basically, it allows the current to go through, the electric current to go through, okay. And guys, when it comes to these electrochemical cells, do not cram that the anode is always on the left and the cathode is always on the right. They can put it anyhow. You need to see what is happening in there, okay. And you need to know by using your tables which one is the reducing agent, which one is the oxidizing agent, which one is oxidized, which one is reduced, and that will tell you where you have your anode and where you have your cathode. But do not cram and say the anode is always on the left, the cathode is always on the right. They will catch you out. Okay, so that's the function of the electrode Y. It is a conductor allowing the flow of current. Now 8.2.2, the half reaction that takes place at electrode Y. Okay, we can see it goes from 3 plus to 2 plus. So let's have a look at our table. Do we have something like that? Can we use something like that? Okay, so iron is being reduced. I don't know if you can see it, but there we go. Okay, so the half reaction, if you have something on your cathode, so whatever is on the cathode side, guys, you write it straightforward, okay? But if it was on the anode, we would have had to swap this equation. We would have had to start with iron 2 plus. But on the cathode side, you write it exactly as it is given in the table. Okay, so that is the half reaction that occurs. Okay, let's go back to question 8. Yeah, so that's the half reaction that takes place at the cathode. Okay, because you can see it goes from iron 3 plus to iron 2 plus. All right, and now 8.2.3. The net overall equation for the cell reaction that takes place in the cell. When they say the net, okay, it means without the spectator ions. But in any case, they didn't tell you in the solution what we have there. Normally, you would have like sulfate and yeah. But yeah, the net overall equation of the cell for the cell reaction that takes place. So what do I do, guys? Normally, I would write down what happens at the anode, okay? So I would write down the oxidation reaction, half reaction. Okay, I know I had zinc as a solid, and then it went to the ion zinc. Okay, then I know I went from iron 3 plus that electron, and we go to iron 2 plus. Okay, guys, so here for the zinc, we have 2 electrons. Here we have 1 electron. So this formula, because I need to balance, okay, this is where maths comes in. I need to balance. So for this reduction, I forgot to write there. This is what occurs at the reduction. So I need to multiply this by 2 to balance it. And here I'm multiplying by 1 to balance it. Okay, I hope you guys are getting me and you're understanding. Okay, so at the end, what then happens? So zinc will stay the same. Okay, I have my solid. And iron, because it's multiplied by 2, so iron 3 plus has to be multiplied by 2. I'm not going to put the electrons. You know, if I multiply by 2, it will be 2 electrons on the oxidation side. So they will cancel. So I don't put electrons in. Okay. So then it goes all the way to zinc 2 plus, and I multiply the iron by 2. Okay, so that is the net equation for the cell reaction that takes place in this cell. Okay. All right, so now 8.3, calculate the initial EMF of this cell. Okay, because they told us that it occurs under standard conditions, we can then put that 0 there, that exponent 0 or O or whatever. That is what it means. Okay, standard conditions apply. All right, so the formula that you would use, I hope we have it. Yes, we do. So I'm going to go with the first one where it says the cathode minus the anode. Minus E anode. Okay, and basically what happens at the cathode, that is where we have our iron 3 plus going to iron 2 plus solution. Okay, so we have 0.77 for it. Okay, and at the anode we have the zinc. All right, where is the zinc? There's the zinc, which is negative 0.76. Okay, guys, the one thing about galvanic cells, you should always have a positive number for your E cell. If you do not get a positive number, you did something wrong. So minus minus becomes a plus, 0.76, so we have 1.53 volts.
Mommy.
Okay.
Mom.
Okay, sorry about that. Okay, the final question. How will the initial EMF of the cell be affected when the concentration of the iron 3 ions is changed to 0.6? Remember, under standard conditions, your concentration is 1 mole per cubic decimeter. So now we went from 1 mole. Okay, let me just put the 8.4. Let's go a little bit up. So our concentration, we went from 1 mole per cubic decimeter to 0.6 mole per cubic decimeter. So we reduced. They're expecting you to know that the under standard conditions, the concentration is 1 mole. So it reduced, right? That is the iron 3 ions. So what do we do here? Okay, so the concentration of this reduced. Okay, now what happens? According to Le Chatelier, okay, on your reactant side, if there is a reduction of any of the reactants for a new equilibrium to be reached, you need to now, your reaction will be reverse, it will be a reactant favored. Yes, I wanted to say reverse favored. Okay, so if the concentration of your iron 3 plus ions reduces, according to Le Chatelier, your reactants will have to then be increased, okay, for a new equilibrium to be reached. So our ions reduced, right, in concentration, so it will then be reactant favored. Okay, so the arrow there just means it will be reactant favored. Okay, according to Le Chatelier. I'm not going to write all of that. Okay, according to Le Chatelier. Okay, so what then happens, guys, when you have a reactant favored condition? Okay. Again, sorry about that, guys. I'm recording on a Sunday before going to church, so it's quite hectic. Okay, so the rule of thumb, okay, is if you have a product favored or forward reaction favored, okay, so after you check out what happens to the conditions, in our case, the reactants, the concentration reduced, so it had to be reactant favored or reverse reaction favored. Okay, so if you have a forward reaction or product favored, what will happen is your voltage reading, okay, it will increase, or rather your E cell will increase. That is what happens. But if you have reverse reaction or reactant favored, in our case, then your voltage will decrease or your E cell will decrease. These are things that you should remember. Okay, this is the theory that you should remember. Please engrave it in your minds. Okay, cement it in your minds. Do not forget this. Okay, so in our case, like we said here, the iron 3 plus concentration reduced. So according to Le Chatelier, your thing became reactant favored. And then what will happen is your reading, as you see on the cell, okay, your voltage will actually decrease. So they say, how will the initial EMF of the cell be affected when the concentration of iron 3 ions is changed from 1 to 0.6 mole per cubic decimeter? So I know it's 1 mark. I'm explaining a lot, but I need you guys to understand. So choose from increases, decreases, or remains the same. In this case, guys, it decreases. That is the answer. Okay, let me just position myself. It decreases. Okay, and this is the explanation why. Okay, so you need to, this is why it's important for you guys, for your net overall equation, for it to be correct. Because if it's not correct, yeah, I don't know how else you would write this out nicely. But this helps you to see what happens on your reactant side, what happens on your product side. Is it forward, forward favored or reverse favored, So that actually helps to answer this question. But please do not remember this rule of thumb, guys. Important. And we are done with question 8. I hope you guys learned something. I hope your preparations for your final exams are going well. And please do not forget to like our videos, subscribe to our channel, share this information, guys. It's very key. It's very helpful, really. It really is. So yeah, we're doing this to serve you guys. So please share this information. And if you want tutoring from us, go to our website, www.mvtutors.co.za. Make a booking with us. Get to our free consultation, book for a free consultation with us, and show your parents these videos to say, Mom, Dad, they do know what they're doing. Can I please have a session with them? I need this. Okay. But yeah, bye. That's it from me. Let me go to church. Hello everyone and welcome to MV Tutors. I'm Tsulu and I'll be looking at question 9 of the chemistry prelim that was previously written in the Gauteng province. Okay, so what does it say and what does it want from us? Alright, so the simplified diagram below represents an electrochemical cell used for the purification of copper. The impure copper contains small amounts of silver and zinc as the only impurities. Okay guys, so what happens actually here? When you have, or when you want to purify copper, okay, I'm just gonna draw again, or maybe let me just sketch here so that we can see what's going on. All right, just bear with me. Okay, so when you have impure copper, as they said, there are impurities such as silver and small amounts of silver and zinc, okay? So on the anode, that's where you have the impure copper, all right? And on the cathode, you actually have the pure copper, okay? Remember, with an electrolytic cell, the anode is actually positively charged and the cathode is negatively charged. The electrons flow from the anode to the cathode, okay? So the anode, that is where oxidation occurs. And at the cathode, that is where reduction occurs. Okay, so your impure copper with the electrolyte that you have, okay, they will be inside here. So from your impure copper, as it is oxidized, you will have copper 2 plus ions, okay? And those copper 2 plus ions, remember you also have zinc in this solution, okay? And what happens to your silver? Well, silver will form at the bottom here. It'll become like a sludge, okay? Yeah, it's like a sludge that's just going to settle at the bottom. All right, so what happens really is your copper 2 plus ions are going to be attracted to the cathode, and therefore as your impure copper reduces in mass, your pure copper will increase in mass, because after all, you want the pure copper, right? So yeah, that is pretty much what is happening over here. So let us try to answer the questions. Okay, so now 9.1, they ask, define the term electrolysis. Okay, so electrolysis, guys, this is pretty much a chemical process, first of all. Okay, it's a chemical process whereby the electrical energy converts to chemical energy. Basically, guys, electrolysis, well, you can't have pure copper forming if there isn't any kind of electric current going through it, and that is why we have that DC source. Okay, so your anode, as maybe you might remember, that is where it is positively charged. So your DC source, your battery source, that is where it's positively charged, and where you have your cathode, that is where it is negatively charged. So you need an electric current flowing through this electrochemical cell for the chemical process to occur. So you need electricity for this chemical process to occur. Okay, cool. And so that is electrolysis. And then 9.2, write down the name or formula of two positive ions present in the electrolyte. Remember, I told you that the silver ions, well, silver will actually just settle at the bottom. Okay, it'll become a sludge, and therefore you remain with copper. Okay, in the electrolyte, and zinc. Okay, let me just say zinc. Okay, so those are your two formulas for the positive ions. Yeah, so your two positive ions present in the electrolyte. Okay. And now 9.3, write down the half reaction that takes place at the cathode. Okay, guys, remember at the cathode, you have your pure copper, okay? And what is it? Yes, so the copper ions migrate because they're attracted to the cathode, because the cathode is negatively charged. So they attract there, okay? You might ask yourself, what about zinc? Zinc is also positive. Doesn't it attract there? We are getting to that. I'm glad you asked. But copper is winning in this case, and I'll explain why in the next question. So copper will attract to the cathode, okay, and the cathode will increase in mass. Okay, I really hope you understand it. So what are we doing? We are getting the ions, okay? So the ions of copper form the solid copper. Why? You wanted the pure copper. So when you go to your table of standard reduction potentials, you must make sure you go from ions to solid, and we are dealing with copper, okay, not zinc. So let us go and see. Let's write down the half reaction, but let's have a look at our table here. So we have copper 2. There are quite a few coppers, okay? There's one here, copper plus, okay, plus E. That's not the one we're looking for. We're looking for copper 2 plus, okay? So there's this option here. There's this option here. There's that option there. And there's this option here when it comes to copper. So which one do you choose? You will choose the one, this one. You have an ion forming another ion. We want a solid. Okay, this one, it's just copper plus, but we know we're dealing with copper 2 plus ions. So this is the half reaction we're going to write. Okay, so copper 2 plus, we went from ions, okay, and then it gained electrons. You saw that because it's at the cathode, and therefore you have your copper. So another way I would actually write this, let me put it this way rather. We know that your ions are in aqueous solution, and then you have your 2 electrons, and then we finally have the copper solid. Okay, so yeah, that is that. Let us go back to the question. Okay. Yeah, so now we go to 9.4. And then it says, refer to this table of standard reduction potentials and explain why the purified copper will not contain any zinc. And that is what I was asking you. I mean, here we can see we have positive ions in here, okay, in the electrolyte. We also have a cathode that is negatively charged. Why doesn't zinc form there? Why is it only copper that is forming? And we're going to go have a look at our table of standard reduction potentials and explain why the purified copper will not contain any zinc. Okay, so we are here. So look at copper and where it is. Okay, I chose table 4A. You can choose any table, it doesn't really matter. But here for, okay, so if you look on this side, on the right hand side, here I am pointing, but you can't see. So if you look here on this side, ne? It is increasing reducing ability. Okay, basically your, how do I put it? If it says reducing ability, it's like increasing, your reducing agent is working, okay, in that direction. So reducing ability, think of it as the reducing agent, okay? And if we say reducing agent, basically we're saying it's oxidizing ability. Oxidizing. It can oxidize a lot, okay? And if you look on the left-hand side, increasing oxidizing ability means that it is an oxidizing agent. You know, the oxidizing agent ability of it is high. Okay, so, yeah, my son, please excuse that sound. But yeah, so in this case then, it's reducing ability. Okay, it's, ooh, what did I write there? But yeah, it's reducing ability. Please, yeah, excuse my handwriting there. It's reducing ability, basically, it's high in if you go upwards, okay? But its oxidizing ability is high going down. So we see we have copper here, okay? So it has the ability to reduce, okay? Meaning accepting electrons, meaning gaining weight. But if you look at zinc, where is zinc? Let's go down. Oh, there it is. Okay, so zinc is here. So zinc does not have a high reducing ability. Copper does. And that is why the copper ions, or rather there at the cathode, it is copper that will attach. Okay, the copper ions will attach to the electrode. Okay, to the cathode there. And that is why you only have copper. Zinc, on the other hand, has a lower reducing ability. It has a higher oxidizing ability, okay, as we have seen, okay? So zinc, yeah, doesn't reduce as much as copper does. But how do we put that nicely in words? Okay, let us do that. Okay, so basically then, zinc is a weak oxidizing agent. Than copper. Okay, we've seen it's oxidizing, well, rather it doesn't reduce as much as what do you call this, copper. Okay, remember the one that reduces is the oxidizing agent, the one that oxidizes is the reducing agent. Okay, so please don't confuse. Whenever we say oxidizing agent, you're like, no, but copper oxidizes more than, zinc oxidizes more than copper. Yes, it does, but it is a weaker oxidizing agent than copper. Okay, weaker. Yeah, so zinc is a weaker oxidizing agent than copper. Okay, it doesn't reduce as much as copper does. Therefore, it will, let's go back to the question. Yeah. So that is why the purified copper will not contain any zinc. Okay, zinc is a weaker oxidizing agent than copper. Okay, and therefore, so since zinc is a weaker oxidizing agent than copper, therefore it will not reduce to zinc. Okay, so you will not find on your purified copper, you won't find patches of zinc there. Okay, you won't find zinc there. Now you have an impure copper again. No, it won't. So zinc is a weak oxidizing agent than copper. Therefore, it will not reduce to the solid zinc. Okay, it's only copper that will, because why? Copper has a higher reducing ability, so it will reduce to the solid copper. Okay, I hope you get it. And then 9.5. Wow, that was 3 marks. So yeah, I hope my explanation was sufficient. Okay, now 9.5. Calculate the maximum mass of copper formed if 0.6 moles of electrons are transferred. Okay, so if 0.6 moles of electrons are transferred. Remember copper, we need to go get its molar mass. Do we have the, we don't have the periodic table. Let me get the periodic table and then write down the molar mass of copper. Okay, and then we will see what we can do. Okay, so I found the periodic table, and as we can see, copper has a molar mass of 63.5 grams per mole. Okay, I prefer putting it like this over the moles, and now we need to multiply by the amount of moles of copper. Okay, yeah, so let us get back to that question. Okay, so how many moles of copper do we actually have? All right, so it says calculate the maximum mass of copper formed if 0.6 moles of electrons are transferred. Okay, so guys, just a reminder, here, this is where we have our copper solid, right? Okay, that is where our molar mass is 63.5 grams per mole. But here you have 2 electrons, not 1. Okay, so now if you want to get the number of moles for copper, okay, remember that we had actually 2 electrons, okay, and they told us that the number of moles for the electrons, okay, is 0.6, but we need to factor in that 2 here. We need to get rid of that 2. So, not get rid of it per se. Yeah, but yeah, you are getting rid of it. So if we're dividing by 2, okay, and they told us here, we're going to multiply by a half here because of this 2. Because here, that's just the number of moles for 1 electron, okay? But we had 2 over there, and we had only 1 copper element, if I could say. Okay, so the number of moles of copper then, remember for the electrons, they said 0.6. Then we need to multiply by a half. So we're going to actually get 0.3 mole for copper. Okay, whereas you have 0.6 mole of electrons. So then finally we can calculate. This was just a side calculation. Okay, finally we can then calculate, what is this? The mass, okay? The maximum mass of copper that can be formed. Let me get the calculator. Okay, so 63.5 times 0.3, we get 19.05. So the maximum mass, 19.05 grams of copper. Okay, and that was it for question 9. I hope you learned something that you will take with you and you're preparing well for the finals. Okay, so yeah, please don't forget to like our videos, subscribe to our channel, share this information with your fellow matriculant friends, teachers, parents as well. If you would like tutoring and you want to support why you want to choose MV Tutors as your tutors. All right, guys, bye. Hello everyone and welcome to MV Tutors. I'm Tsulu and I'll be looking at the final question of the prelim chemistry paper written in Gauteng. Okay, so let us see what do they want from us. Okay, so question 10, consider the table of standard reduction potentials below. Okay, I don't know if you can see the trend, guys. If you were watching question 9, we did discuss a little bit the trend. Okay, let me take this a bit lower. Okay, so basically, if you look at zinc here, we said that zinc, okay, I'm just using this as reference to question 9. Zinc actually oxidizes more than copper, okay? So the oxidizing ability in this direction increases. So oxidation increases in this direction, and copper reduces more than zinc. That is why you could purify copper. Okay, so in this direction, reduction increases. Okay, so basically here your oxidizing agent, oxidizing agent is working hard. Okay, in this case your reduction or your reducing agent is working hard. Okay, so we can see relatively what's happening here. Okay, as you go up, oxidation increases, oxidation ability increases, if I could say. Okay, and as we go down, then reduction ability increases. Okay, bearing that in mind, looking at our table of standard reduction, you can even see on the tables provided for you at the back of your exam paper, table 4A, is this part of table 4A or 4B? Okay, but since we just did question 9, well, if you watched the video for question 9, you would know that which way goes where. All right, so now the first question, they say define the term reducing agent in terms of electron transfer. Okay, so before we even define it, I want to remind you, okay, that where there is oxidation, okay, where there is oxidation, if you look at an electrochemical cell for one, your anode, that is where oxidation occurs. Where oxidation occurs, basically you have your reducing agent there, okay, and where reduction occurs, that is where you have your oxidizing agent. So now when they say define the term reducing agent in terms of electron transfer, so what I'm expecting for the reducing agent, I'm expecting the reducing agent to lose electrons because that is where oxidation occurs. So that is what you would actually write. But for 2 marks, I would say a reducing agent, okay, so a reducing agent is a chemical compound. If you want the very formal definition, so it's a chemical compound that is oxidized okay, therefore losing electrons. Yeah, it is a chemical compound that is oxidized and loses electrons, not losses, loses electrons in a redox reaction. Yeah, but the whole thing of a reducing agent is basically loses electrons. That's what they really wanted. Okay, now 10.2. From the above table of standard reduction potentials, write down the name or formula of the strongest reducing agent. Okay, so we already Well, pretty much by drawing the arrows that we did using the reference of zinc and copper, we know chromium there. Okay, strongest reducing agent, it would have to be chromium. Okay, Cr. Name of formula, so I would say chromium. Okay, that's 10.2.1. 10.2.2. Okay, so write down the oxidation half reaction with the lowest oxidation potential. Okay, so if we look at it, guys, where reduction occurs, okay, so when reduction is increasing, it means the oxidizing potential or the oxidation potential is low. Okay, so chromium, like we have seen, its oxidation potential is the highest, okay, but its reducing potential is the lowest. But it being a reducing agent, it's like the best. I hope I'm not confusing you. So when you look at chlorine, okay, chlorine, it reduces very well. Okay, so its reduction potential, it is the best. Its oxidation potential, the worst, but as an oxidizing agent, it is the best. So what are they saying? Write down the oxidation half reaction with the lowest oxidation potential. So that would have to be chlorine. Okay, and because it has the lowest oxidation potential, okay, yeah, so the way it is written there, you're gonna have to like swap it around, okay, because it has the highest reduction potential. So you're gonna start with your iron, which is 2-chlorine, okay, and then it goes all the way to chlorine gas. Okay, this is actually aqueous solution. So chlorine gas plus 2 electrons. I hope I didn't lose you guys there. Okay, so the lowest oxidation potential, definitely chlorine. All right, and yeah, 10.2.3. All right, so write down the reduction potential of the half reaction in which chromium 2 plus acts as a reducing agent. Okay, so I'm going to try to put the chromium 2 plus on the left hand side and everything else on the right. So first of all, we have chromium 2 plus, okay, plus 2 electrons, and we get chromium. Okay, let me just read the question again. Yes, for chromium 2 plus. And then the other chromium 2 plus that we see, okay, we have chromium 3. Okay, so let me just highlight them so that we are seeing the same things. Okay, so first of all, we have this chromium 2 plus. This is what we have written down. Then we have this chromium 3 plus, but there is no chromium 2 plus, so we're not considering that. Then there's another one, chromium 3 plus and a chromium 2 plus. So like I said, I'm going to swap them around, okay? So I have chromium 2 plus, which goes to chromium 3 plus an electron. So what happened in both cases, guys? I just want to get green. Okay, so here we went from having 2 excess protons, right? And we went all the way to 0. Okay, so basically we gained electrons here. Okay, so here we gained electrons. And if you gain electrons, it means we went through a reduction. Okay, so it was reduced. Chromium was reduced. Okay, and since chromium was reduced, yeah, so that is reduction that occurred there. Okay, and reduction, basically chromium was the oxidizing agent. Oxidizing agent. Okay, then this chromium here lost an electron. Do you see? Because it became more positive. There are more protons than electrons. So it lost an electron. Okay, meaning it was oxidized, meaning this is the reduction or reducing agent. Okay, now I forgot the question. What were they asking? So they're saying the reduction potential of the half reaction in which chromium acts as a reducing agent. Okay, so we see here chromium acts as an oxidizing agent on top. Okay, so here it acts as an oxidizing agent, but here it acts as a reducing agent. Okay, so we have our chromium that we're going to use. Okay, and if you look closely, it's this one here that we're going to deal with. Okay, so the question there was, they want, write down the reduction potential. Okay, so the reduction potential is going to be negative 0.41. I think for me that's just an understandable way of the answer, of writing down the answer. If you have a shorter way of doing it, by all means. I mean, you can have a look at both of them. Like we said, yeah, actually it's better this way, for me personally. A way of answering it. It's only 1 mark, but I just wanted you guys to understand how we get to the answer. Okay, now we get to 10.3. So now a learner pours a copper 2 sulfate solution into a zinc container. Okay, so there you have a zinc container. Just gonna make it a little bit thick. Okay, and we have zinc there. Just gonna, so that I can write. So we have zinc. Okay. This is a solid zinc, ne? Okay. So now, what happens? Okay. So now, this learner pours copper 2 sulfate solution. Okay, so copper 2 sulfate, so we have copper 2 sulfate. It's going to be like that, okay? Because copper has 2 plus and sulfate has 2 minus, so it's fine. Copper 2 sulfate, so that's the solution in there, okay? We have some copper 2 plus, we have some sulfate 2 minus. Basically duplicated all over the show. Now they ask in 10.3.1, is a zinc container suitable to store a copper 2 sulfate solution? Okay, is it? Is it suitable? Okay, I don't think it is, guys. No, I don't think zinc is a suitable. Remember, zinc has a higher oxidizing potential, so oxidation potential. It does not mind giving away its electrons, okay? Whereas copper, it has a low oxidation potential compared to zinc. So zinc doesn't mind giving away its electrons, and when it gives away its electrons, it will form zinc ions. Now those zinc ions in that solution, now you're gonna, in this whole mix here, you're gonna have zinc ions, okay? They've joined the mix, okay? And what these zinc ions will want to do, they will want to combine with the copper, with the sulfate, okay? And it's going to want to form zinc sulfate, okay? So anyway, 10.3.2 asks us to explain. So everything that I've just said here. But let us find a way of writing it nicely. Okay, so let us write this down nicely. So explain the answer to question 10.3.1 by referring to the above table. Okay, again, looking at this, we have said that zinc, okay, so zinc oxidizes more than copper. Okay, so therefore, you will have your zinc solid, right? And looking at our standard reduction table, it will then form zinc ions. Okay? That's basically what's going to happen. And now, your solution, basically, your solution will contain zinc ions, copper ions, and sulfate ions. Okay? And because zinc has a higher oxidation potential, because zinc has a higher oxidation potential, it will then connect more with your sulfate. Okay, so there will be a reaction that happens between zinc and the sulfate, and you'll end up having zinc sulfate they're forming. Okay, and it really all has to do with the fact that zinc oxidizes more than copper. Zinc is willing to give away electrons than copper is. Copper is willing to take those electrons, but zinc wants to give away its electrons so that it ionizes, okay, to zinc 2 plus, and in that solution it will then form with the sulfate. Okay, so yeah, I think that is it, guys. I'm not missing anything, but yeah, I hope you learned something. And please, like I say, like I ask, do you like our videos? Subscribe to our channel, share this information with your friends, with your teachers, with your parents. If you do want a lesson with us and you want to motivate your parents, like, Mom, Dad, these guys know what they're doing. Can we please organize a session with them so that I can make sure I pass my metric very well? Okay, other than that, it is it from me. Enjoy the rest of your day.